Okay, good morning. Welcome to day 2 of OARC Spring Workshop in Amsterdam. For those of you who have just arrived today, I'm Keith Mitchell, OARC President. So we have another full day of presentations today. I just wanted to do a few quick announcements.
Let's disappear again. All right.
Thanks, Paul.
Yep.
First of all, big thank you to SIDN for sponsoring last night's social. I certainly enjoyed it. I hope you did as well. Also, thank you to our other sponsors. Sorry, bear with me a second. So yeah, just a few quick announcements to repeat what I said yesterday morning. Wi-Fi, use the OARC or OARC AS's IDs if you can. The morning and afternoon coffee breaks are in the adjacent room. The lunch will be in the foyer. The toilets are just opposite the registration desk. During lunchtime, if you specified any dietary requirements, please just let the hotel staff know, and they will guide you. In the event of a fire alarm, we are to await instructions, and the staff will confirm whether it's a valid alarm and what to do in that case. We're doing a PGP signing session at lunchtime. If you want to participate in that and you didn't already send your key to pgpsign@dnsoarc.net, please do ASAP. Matt Pouncett will be running that, and that will be in the Merriman room opposite the lifts. Badges, if people who have a red lanyard are members of OARC staff, board or program committees, so if there's any help or any questions that you have, we'll be happy to help out. People with a blue lanyard are first timers, so again, welcome, and I'm sure that everyone else, all the usual suspects, you'll do your best to make the first timers welcome as well. And at the end of the day, or when you leave, please can you return the badges to us. We're webcasting. The video for yesterday's is already available on the OARC YouTube Google Plus channel. That's the URL for today's sessions. And for remote participants, there's a Jabber room, which is running on the usual location in the OARC server. I shouldn't need to tell you this, but all the beeping. I know that we have 1.5 devices on the Wi-Fi per attendee, so please make sure that your 1.5 devices are suitably muted. And obviously, as a courtesy to people in the webcast, when you're answering a question, please wait for a microphone or come up to the microphone at the front, and please identify yourself and affiliation. And we're on the usual social media hashtags. And thank you to all our speakers yesterday for keeping on time, and for all the speakers today for getting your slides uploaded in advance. That really helps us run smoothly, so thank you for that. So I just wanted to finish off by thanking our sponsors. Again, SIDN is gold sponsor and for last night's social. VeriSign is gold sponsor, Comcast is silver sponsor, Nominum is bronze sponsor, and NZRS is contributing sponsor. And for all the North Americans here, don't forget to phone your mom today. So I will hand you over to Paul Ebersman, Program Committee member and the session chair for this morning.
Thanks. All right, so first session today, the theme is going to be DNSSEC, and let me get the slides up. First up in the queue is Jeff Houston from APNIC, and he's going to be talking about the ECDSA algorithms and penetration thereof.
Thanks, Paul. Sure. Hi, I'm Jeff Houston. I'm with APNIC, and
This is a presentation on some work that we've been doing over the last sort of 6 months and looking at the level of support for elliptical curve cryptography as an alternative to the widely used RSA cryptography. Why do we look at this? I'm no cryptographer, you know, ones and zeros are just ones and zeros to me, so what the hell. But the folk who are meant to know this stuff, whom I've got no option but to trust, tell me that ECDSA gets you around 10 times the cryptographic strength in the problem that it presents for the equivalent number of bits. I translate that as being, it's really good foo, you know. And the other thing about this is if you are sort of looking at, say, the equivalent of a 2048-bit RSA problem, you can squeeze that right down in ECDSA. So you can get actually a much smaller SIG. Now, you kind of go, well, that's cool, but so what? But the so what is actually all about the DNS. Because when you look at the DNS itself and you look at the fate of fragmentation in UDP, and you look at protocols like V6, where fragmentation is a backward signal, not a forward signal, all of a sudden this is a really, really big issue. And the sort of survival rates when you start fragmenting tend to get a lot lower. So this is not a presentation on survival rates. I'll save that to next time because we're looking at that too. But this is really just a presentation about ECDSA itself. So here is a quick bench test. Exactly the same problem space, ECDSA signed, RSA signed, there's a dig, 527 bytes in ECDSA, 937 bytes in RSA for the same question under the same circumstances. So, you know, in theory, you can manage to get responses way down by using ECDSA. And if, is anyone still running a V4 system that won't accept a packet longer than 576 octets? You know, that old RFC 1123 thing? Because if you were, that one will make it, that one won't. You know, the old V4 standard said, no matter what else, you've got to accept 576 octets. After that, it's anyone's guess. Well, we've gone past that for most of the time. But when you start talking about larger than that, above 1280, the whole V6 thing comes along. So this is just really good foo. You know, let's just go and use ECDSA for DNSSEC. This is wonderful, yeah? So all of you support it, right? If I signed an ECDSA, would you understand me? That's a really, really good question. I've done a few of these talks and they all sort of sit around a common theme that what I'm trying to do is to not bench test. George and I in APNIC are trying to look at the internet from the user. And the best way to actually look at the user perspective is to get the user to actually execute your test. And the problem with getting the users to execute their tests is that they won't, because they're bastards. And as you may have noticed with the Chinese Great Canon of the last couple of weeks ago, one of the best way of co-opting these bastard users to doing things is to embed code in JavaScript inside an ad, which we do. So this is done with Google's kind support, and we thank them. And I promise there's nothing malicious in here, and there's no endless loops of denial of service, which is a serious issue. Honestly, it's a serious issue. So what we do is instead of doing a few million tests, we do exactly 5. So when the ad is impressed, you don't need to click anything. These 5 things fire off, and they all involve getting a URL, but the DNS part of that URL is doctored. They're all unique URLs, so caching doesn't work. The first one, there is no DNSSEC. The second one, RSA based. The third one, just to make sure we're on the same game, is a deliberately broken signature in RSA. So if your validators are good, all of them should be giving you back serve fail. You should not get an answer. You should not get that URL. And just to make sure now we understand what we're doing, we then go into the ECDSA. 4th one, signed correctly. 5th one, signed badly. So that's sort of what the thing looks like. Huge front end just to make sure it's long enough with a few bits and pieces to detect middleware, proxies, online stalkers, and all the rest of the shit that inhabits the internet, and there is a lot of it. So I'm interested in the first time this unique URL is presented to me, not the 20th. Thank you, NSA. And so those strings kind of tell me when the ad was created and let me know when the first impression happened. And sort of unique sign zone. So we run this stuff with enough there to make sure we actually follow the validation downwards through a uniquely signed zone, ECDSA signed and ECDSA signed badly. DNS is really, really simple, isn't it? You ask a question, you get an answer, right? Well, obviously, that's the protocol, isn't it? And of course, DNSSEC is also really, really simple. You ask a question, you get back an answer in some SIGs, you start validating the SIG. So what do? You ask the parent for the hash of the zone signing key, the DS record. Then you go back down to the zone and get the DNS key. Life is wonderful. That's what happens, right? Yeah, right. So this is what I expect to see. Single question, 3 answers, if it's all validating. That's what I expect. Never happens. Never, ever, ever happens. Because resolvers are not just obsessive compulsive, they're insanely concessive compulsive, and they worry so much about millisecond gaps, they're aggressive in questioning again and again and again. And just to make life truly awesomely weird, sometimes the front end of the resolver is not the same as the back end. Google, for example, is kind of all 8s at the front end, but another 30 odd IP addresses at the back. Knowing which backs refer to which fronts is always a problem. You know, I see questions that the end of the forwarding chain asks me. I don't actually see what you did as a client. I don't see the resolvers in the intermediates, in the intermediate bits. So with all of these timers and abandons and retries, you get weird crap. So I think this is Ecuador. If someone can tell me where 200.55.224 lives, you know, it's somewhere on the planet. And they asked me for an A record, they asked me for a DNS key record, they asked me for a DS record, but they didn't like the answer. So they go to Google. And a slave of Google asked me for an A record, then a DNS key record, sorry, DS record, then a DNS key, and then a DS and then a DS. What, didn't it like the first one? The next slave, which is the beginning of the clue, asked me for 2 DNS keys only. So you start to see how Google works. When Google's sort of brain inside a POP has a problem, it asks a bunch of validating questions, but they get farmed out to different slaves at different times. And so when you're sort of reconstituting reality, you see in that Google stream, there's a whole bunch of sort of things that look slightly out of order. The original resolver still didn't like what it was seeing, so it asked me for the A record with the DNSSEC okay. It asked me again, just to be sure. Then it decided to turn off all EDNS 0. Then it decided to go and get the DNS key because, you know, you never know. Things might have changed. This is the shit you guys write, you know. This is what you've done to me. It's all your fault. No one else to blame. And so what I'm trying to do is sort of create the stories of what happened, what was going on to cause this. So the first thing I do is give up, right? Just give up and do really simple counts. If you are validating and you understand what you got, you should fetch the DS record and the DNS key record. If you don't know the algorithm, you shouldn't do all of that. At some point you should give up because it's kind of, well, I don't know what algorithm you're using. There's no point getting stuff. So in the statistics, what I saw was I tried this 12 million times because, you know, you can never be too sure. And of course, the beauty of Google Ads is there are 3 billion of you out there. That's 12 billion unique users because Google keeps on getting new people to present the ad to. Thank you, Google. It's wonderful. It's the most sophisticated machine on the planet, I think, delivering online ads, but that's a different issue. Of those 12 million, a huge amount queried for the DNS key RR. That's an awful lot of folk starting the validation dance. So if someone tells you that DNSSEC isn't deployed, think again about that. 1/4 of all those queries, those completed experiments, asked for the DNS key resource record. There is a shitload of DNSSEC out there, a huge amount, around 1/4 or a little bit more. That's for RSA. For ECDSA, mumble slightly less, 20%, 1 in 5. So there is a quantitative difference by just the straight stats. And so what it looks like is, 1 in 5 folk that fetched RSA did not fetch the ECC equivalent, the DNS key. So maybe ECC is kind of an 80% problem, and the other 20% of folk who do RSA don't do ECC. That's good, because in September last year, it was worse. 1 in 3 folk that understood RSA didn't understand ECC. So, we are getting better at this, and that's kind of good. So let's just do a little more checking now to understand if those gross stats can be actually tracked down into individual behaviors. So the first kind of question, because I don't write resolver code, so I don't bloody know, when and how do you recognize the signing protocol? Because when you get back the resource record signatures, it has the protocol field. And so if you don't do protocol 13, it's not much point going any further. But I could be lying. There could be a man-in-the-middle attack that's changing the protocol field. So maybe you want to fetch the next thing, the DS record, just to make sure that what you're seeing is real. Or maybe you should do all the fetches and then go and check. So 12 million experiments, 2.9 million fetched the ECDSA DS record, and only 2.4 million fetched the DNS key. So it looks pretty strongly that no matter what you get back in the RRSIG, you always fetch the DS record and then figure out whether you can go any further. And the DNS key is the one that says, support the protocol, don't support the signing protocol. You guys write the code, you should either be nodding or violently disagreeing at this point, because I just see this from behaviors. I have no idea what your code does. Thanks. So, is this right? Is this behavior standards conformant? So, you go back and dig in the RFCs, and that's what it looks like. This is RFC 4035 in its original version. This is the translation. The translation says, if the DS record, and it is the DS record in the RFC, if you don't support any of the protocols listed in your fetch of the DS, give up and treat it as unsigned. So don't not send an answer, send an answer, but treat it as if it's unsigned. So when you get these DS records with an unknown crypto response, basically what you do is that third option. You just abandon validation at that point and just return the unvalidated query result without the AD bit set. Couldn't do anything about this. Here, have it your way. I have no idea. So how does this relate to users? Now I'm going to look at the next thing, which is looking at how many folk fetched the web object. Because I'm really interested now in understanding that badly signed ECDSA. Obviously, this is someone mucking around with the crypto, but if you're treating it as unvalidated, you're just going to accept the answer and go and get the web block, right? Right. So DNS data collection, 2 million folk appeared to basically be exclusively using RSA resolvers. If it's badly signed, they didn't get it. If it's well signed, they got it. So of those 2 million folk, I need glasses, this fine font. Of those 2 million folk, what did they do? 80% of them, 4 out of 5, correctly handled ECC. So they got the well-signed object, they did not fetch the badly signed object, and they correctly pulled down both the DS and DNS key resource records. The failure modes are uniquely bizarre. There's some that obviously did no ECC. They sort of saw and fetched and they did the right thing. Some of them, although they did the full dance in RSA, did nothing in ECC. They sort of went, oh yeah, fetched the A record, looked at the RRSIG, and despite what the standard says, just went and fetched it anyway. Some of them's kind of used a mix of resolvers. So the failure rate in ECC is still around that 20.1%. So of the folk who correctly do RSA, 1 in 5 incorrectly handle ECC insofar as true correctness is, I won't hand you back invalidly signed. These folk look as if they're obeying the spirit of the original RFC, that lot. The others are kind of obeying the intention, but not the precision of the way it actually is meant to happen. Still the same issue, they fetch it, but they should, not quite sure why. So, 80% of clients exclusively use validation in RSA, do the right thing in ECDSA. 2/3 of the result do the right thing and don't fetch any DNS keys. The remainder kind of do weird stuff. They get back the serve fail. So their first resolver says, this is ECC, I understand it, this is badly signed, I'm not going to give you a result. And then unlike RSA, they then head over to a non-validating resolver that simply says, here's an answer. Because that second resolver that they use for ECC doesn't do any validation whatsoever. Where are they? Where are these folk who fail? 5,600 samples in Cyprus, 94% of them failed. Malta, Barbados, Georgia, South Africa, Australia, Yemen. It's sort of a strange list. Canada's in there somewhere. 40% failure. I don't know why it's kind of this aggregation by country, but you know, maybe it's not country, maybe it's your ISP. So here are the ISPs that are running RSA validating resolvers, but they basically fail in ECDSA. So Viasat, VIP Mobile, Telemac in Slovenia, Kyushu Telecommunications in Japan, Microplex in Australia. So some of these aren't fools and they're, you know, not small. So if you're on that list, I know you, you know what you're doing, you're not doing ECDSA. Which resolvers? Those are the resolvers that appear to fail. So that whole all fours level 3, anyone here from level 3? You got a problem. Some from Indonesia, etc. Oh, and ChinaNet backbone, because they don't like ECC, evidently. So why aren't they supporting ECC? You know, what's going on that they're not supporting it? Well, again, I haven't written a resolver, but the ones who have all appear to make extensive use of the OpenSSL library. Not quite all, but a lot, right? And maybe the real question is, what's going on with OpenSSL and ECDSA? Well, that's really easy to answer. This is all IPR lunacy. So, you know, the whole Certicom thing and this whole issue of lawsuits and who owns ECDSA and who has patent rights appears to have been a really big factor in the way in which these libraries have been constructed with support for ECC or not. And so what has happened is that ECC support in those libraries is relatively late. OpenSSL included it only from 0.9.8, but that's OpenSSL. Certain bundling of those products, and a lot of you use, you know, Linux, Red Hat or whatever, still compiled with it off for quite some years thereafter. And what you deploy in your DNS servers, well, what ISPs deploy in their DNS servers, is a bit like Power DNS 2.6, wasn't it? 2.9. That's the one. I think there's an OpenSSL problem of the same kind of dimension of just this trailing lag of old libraries and old stuff sitting there in deployed resolvers that just don't keep up to date. And so you sort of get to this question that we just can't keep on adding the bit length of RSA, because going past 1280 is bad. Going past 1500 octets in a DNS response is kind of really interesting. Really interesting if it absolutely definitely has to make it and it's trailing frags, you're stuffed. Because absolutely definitely has to make it for responses longer than 1500 isn't true. There will be casualties. So ECDSA looks really, really cool. It's short, you can go to much better cryptography and keep the length down. But with 1 in 5 folk going, oh, no, just going to go into unprotected mode, maybe that's not good enough. On the other hand, I was reading Cloudflare's blog, and they said, oh, well, we're going to sign everything. And I thought, oh yeah, they've given me an example. What's the example? Well, the example, the Cloudflare use is protocol 13, ECDSA. There's the question, there's the response, the answer, 261 octets. Brilliant. Thank you. Questions? There's a microphone just here. I'm like,
Hi, Jeff. Antoine Schuren. Can you go back to slide 17?
I don't know, are they numbered?
Well, it's just before the RSC stuff where you... Yeah, this one. You said that you assume that, you know, if they don't understand the algorithm, you fetch the DS, but you don't fetch the DNS key, right? That's the assumption. Now for ECDSA, this is correct. But when I look at the RSA numbers, there are more people fetching the DNS key than the DS. Why is that?
You know when I said that you folk wrote crazy code that just did weird shit all the time? That's an artifact of that.
Or is it caching? Because the DS may be...
No, there's no caching on this stuff. All these are unique. However, I operate the whole experiment, this one, from a machine in Dallas. And so if you happen to live in South Africa or in Australia, the RTT of your queries is getting long-ish. And your aggressive timeouts going, I'm going to wait for, well, I'm going to be really nice. I'm going to wait for 50 milliseconds before I ask again. Well, you know, obviously, question, 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 question. So what's going on here is the fact that around when I looked at this, only 3/4 of the world do a single query and an answer and walk away satisfied. The other quarter go, no, not enough, and just ask me more questions for the simplest of problems. And I think that's why we're seeing this.
Okay, and have you calculated that in your results? That same issue might be there with ECDSA.
Right, so this is why I try to talk about experiments, not queries.
Okay.
So, you know, all the questions from one experiment, you put a lump together and go, that's the result for that user.
Hi,
Hi.
Jared Moss from NTT. Can you go forward a few more slides to where our name is listed for the not supporting ECC?
Yeah, cool.
Yeah, right there, number 8.
NTT, number 8. Yeah.
Yeah, number 8. So is there anyone here from Newstar? Okay, well, so that's actually an IP address assigned to an unnamed customer of mine.
Fix it. Fix it. Use a more recent OpenSSL library. Fix it. Hi, Roy.
Hi, Roy Adams, Nominet. A quick question about the code that you've used to on the server side. How many instances, how many servers do you actually run from Dallas? Is it 1 or N?
We run a single FreeBSD server running bind 9 point something or other. 11.
Okay.
George runs.
So George.
Yes, ask George the next question. It looks like being a tough one.
That single FreeBSD box, how many IP addresses have you assigned to that? Is it 1? Just 1?
Have we split the IPs between different parts of this experiment? No, I think it's one IP binding. So it's all 4 or 8 threads in bind back to the same IP.
Okay. Now the reason I'm asking this is if you happen to have more IP addresses configured, you can actually see if there's still some evidence of rollover and die, which is a thing that you did a couple of years ago. In fact, when you see Servil, right, or when a system responds with bad stuff, you see old resolver still needing to do rollover and die.
If the IP is explicitly listed as NSs, then we would see rollover and die because it walks to the other NSs.
Yeah.
So what we've done,
Hence my question.
so what we've done deliberately is set a single flat zone with 500,000 entries and timed Google's ad system so that the TTLs are comfortably a lot lower than the roll. And there's just a single level, if you will, of checking validation. to check for evidence of rollover and die, which is really useful as someone here is talking about rolling the root key. If you really want to understand what happens with rollover and die and the residual rates, I need a couple of levels of uniqueness to get rid of all the caching. That means I'm going to need some help in machinery and memory to set up the experiment. But, you know, if someone wants to play with me on this and go and look for residual rollover and die, Roy, and has machinery they can help me with, Roy, George and I would be happy to play.
Well, George, Jeff, I'll help you out.
Thank you.
Let's talk in the lecture
Sure.
somewhere. Thank you.
Thank you.
Brilliant presentation. Thank you.
Okay. Thanks.
Thank you.
All right, and next up we have Dwayne Wessels, who will be talking about root ZSK sizes. And let me get the slides up for that. You should be good to go.
Thanks, Paul. So this presentation is about traffic effects of changing root zone keys. The main motivation for this is that VeriSign has begun investigating requirements and consequences for increasing the size of the root zone signing key. There's also, this is also sort of relevant because, as you know, there's a design team now talking about changing the key signing key. So in this presentation, I'll talk a little bit about both of those, but specifically what I wanted to understand was how those changes would affect things like response sizes, bandwidth to root servers, the amount of truncation, and the amount of fragmentation. So this slide has a lot to say about the background for the zone signing key. I'm going to sort of skip over this in the interest of time, but you can come back to this and read it if you don't already know some of this stuff. I do want to say, however, that in this presentation, I present sort of a number of scenarios of different ZSK lengths and changing the root zone DNSSEC algorithm. But just to be clear, at this time, VeriSign is not advocating for ZSK lengths beyond 2048, and VeriSign is also not advocating for changing the root zone algorithm at this time. So the current state of things is that the root zone KSK is 2048 bits. Its rolling frequency is undefined because it hasn't been rolled at this time, and signatures generated with this key have a validity period of 15 days. The ZSK, on the other hand, is 1024 bits. It's rolled every 90 days, every quarter, and has a 10-day signature validity. So this lists the scenarios that I sort of simulated. Did a bunch of tests increasing the ZSK length from values ranging from 1024 to 4096 bits. There's one scenario of rolling the root zone KSK using the same algorithm and the same sizes as is used today. And there's a couple that simulate changing the algorithm from RSA to ECDSA. So the way I did this was created a bunch of copies of the signed root zone with various sizes and lengths and so on. Each root zone is served by its own named process listing on a loopback address. Then I captured a bunch of real traffic from one of our root servers and replayed that traffic, mimicking the query name, the query type, the DO bit, and the EDNS 0 UDP size. So for each query in the input trace, those same parameters were replayed over UDP to all of the named processes and over TCP to all of the named processes. So in my input trace, I did capture TCP traffic, but I didn't replay those TCP queries under the assumption that most of those were there because of a retried UDP query that was truncated, right? So during the replay, I captured these parameters that you see listed here: the DO bit, the UDP size, the response code, the TC bit, and the sizes of the response over UDP and TCP. So in the interest of accuracy, since the root servers also serve the ARPA zone and the root servers.net zone, those were also loaded into the simulation. The ARPA zone is signed with the same parameters as the root zone, but the root servers.net zone is unsigned. This just shows kind of a sample of the output from the tool. The trace file that I took was from March 4th of this year, and matching a root zone file from the same day. I captured 10 minutes of traffic from a route. That was 46 million packets captured, some 23 million UDP queries, working out to be almost 40,000 queries per second. This came from our 5 A route sites at that time: New York, London, Los Angeles, Frankfurt, and Hong Kong. So in the queries, 71% of those queries had the DO bit set and 29 had it not set. In terms of responses, nearly 60% of the queries ended up being NX domain responses, and 40% were either delegations or had data in them. And this last set is sort of interesting. We'll talk about it later. Only 2 out of 10,000 queries were queries for the root zone DNS key RR set. So one thing to keep in mind, all these simulations were done using this version of Bind 9.8.2. It's possible that other server software might behave a little bit differently. I didn't go to the extent of simulating other server software. So here's a little bit more details about the simulations or the scenarios that were simulated. As I said, different ZSK size ranging from 1024 to 4096. In this case, there was just one RR sig over every RR set in the zone. In some of the graphs, these will be labeled as ZSK RSA with a number indicating the size of the ZSK. There's another situation simulated where we're doing a ZSK rollover, just as happens every 90 days. Again, all these are with the current algorithm, RSA SHA-256. The ZSK rollover uses a pre-published method, so all of there's just one RR sig over every RR set in the zone again. The only thing that changes is the size of the DNS key RR set. These graphs are labeled ZSK roll RSA XXX. The KSK rollover simulation is, again, just as it is today. The lengths stay the same. There are 2 RR sigs over the DNS key RR set and 1 signature over all the other RR sets. In the graphs, this is labeled KSK roll RSA 2048. And lastly, a KSK algorithm roll for these 2 ECDSA algorithms. In this case, there are 2 RR sigs over every RR set during the algorithm roll. So this is not really a result. This graph actually shows some characteristics of the client traces. This shows the distribution of EDNS 0 UDP sizes. So as I said before, something like 70% of the queries had the DO bit set, and 90% of those have a EDNS size greater than or equal to 4,000 bytes. So a pretty large receive buffer set. Of the queries without the DO bit set, so DO equals 0, 85% had a EDNS size of 512 or less. So there's a pretty clear split there. This is kind of what we'd expect. The blue line here represents the combination of those two, of the traffic as a whole of both cases. So this graph shows how many UDP responses would be truncated for different ZSK lengths. And truncation here is a characteristic of both the size of the response and the client's advertised buffer size, right? So the situation today is down here. We're returning TC equals 1 for about 0.3% of all queries to the root zone. And if we imagine, changing the ZSK length to 2048, that would go up by about a factor of 3. We'd be truncating about 1% of all queries or responses. And the implication here, of course, is that these would lead to a follow-up query over TCP probably. Not necessarily guaranteed, but that's sort of the inference, right? And so this is not too bad. We don't get sort of, into trouble maybe until we get up to a ZSK length of 3K and beyond. And then it sort of flattens out, again, because most of the queries coming in from clients have buffer sizes that are large enough to handle all of these. Anyway. So this graph, on the other hand, shows how many UDP responses would be fragmented. And fragmentation here is determined by, it's actually pretty simplistic. It's just saying if the response is larger than 1472 bytes, if the DNS message size is greater than 1472, then we would fragment it. So this is a straight Ethernet MTU fragmentation. This is not actually addressing IPv6's 1280 limit. But there's essentially no fragmentation, again, until we get up into the range of 3000 bits ZSK length. So these are actually the only two graphs where I'll talk about ZSK sizes larger than 2048. The rest of them will be limited to 1024, 1536, and 2048. So this graph shows the cumulative distribution of all response sizes for the normal case. So no rolls, just the normal case, but with different ZSK sizes. So the first line is 1024, the next one is 1536, and the third one is 2048. And all of these are pretty well under the Ethernet MTU size, 1500 bytes. Looks like a few of them may be, a little bit above the 1280 limit. But what's sort of interesting is that if we add to this graph the situations where we're rolling the ZSK, the lines are essentially equivalent, right? So the overall size, the overall distribution of response sizes doesn't really change during a ZSK rollover. And the reason for that is because there's really there are so few queries for the DNS key RR set, which is the only one that changes size during the rollover. So a ZSK rollover doesn't really affect the size of responses. Adding to this, the KSK roll, it's the same. So that's this purple line is the one that's new, and it's coincidental with the normal case of a ZSK 1024-bit and a ZSK rollover 1024-bit. So in the big picture, nothing changes in terms of response size, again, because there's so few queries for the DNS key RR set. It's a little more interesting looking at ECDSA. This red line here is the distribution for an ECDSA 256 algorithm. So it falls in between the two ZSKs, the 1536 and the 2048. And the ECDSA 384 line is pretty much on top of the line for a 2048-bit RSA key. And that just sort of works out because the size for, I can't refer to my notes here because this is not PowerPoint, but the size of the signature, the additional signature of the smaller ECDSA happens to exactly match the size of the larger signature for the ZSK, the 2040-bit ZSK. So this chart shows the size of DNSK responses for the different situations. So here's the three normal RSA cases. Here's the rollover ZSK RSA cases. So obviously that The DNS key response gets bigger because it doubles in size. This is for the KSK rollover. This is the only one that exceeds 1280 bytes. And the ECDSA is down here. So again, this is only for the DNS key response size, not for all of them. This shows the percent of responses that would be truncated under the different scenarios. So we saw this in the first graph for the existing RSA algorithm. We go from about 0.3% to nearly 0.1%, and it's the same for the rollover case. For the ZSK rollover case, excuse me. For the KSK rollover case, again, it's almost no change in truncation, and an algorithm roll more or less matches these other ones. This is the percent of DNS key responses only. So the first graph was all responses. This is the percent of only DNS key responses that get truncated. So the situation today is that we're truncating about 2.5%. And if we were to change the ZSK length to 2048 bits, we would be truncating something like 8%. And it happens to match the same for all these other situations as well. Percent of all responses that are fragmented, essentially no fragmentation uncovered during these simulations. And again, percent of DNS key responses that had fragmented, essentially 0. Lastly, this graph represents bandwidth generated by responses for the different scenarios. Today, based on this data from ARoot, that server is generating something like 150 megabits per second of traffic at 1024 bits ZSK. And if we increased it to 2048 bits, we'd expect something like 200 plus megabits per second of traffic. And again, the other ones match because overall there's really no change between a roll and a normal case. So, last slide. In summary, most of the scenarios simulated here show a modest increase in truncation, leading to a follow-up TCP query. Essentially no UDP fragmentation at 1500 bytes, and up to 35% increase in bandwidth in root server from root server responses. So with that, happy to take some questions. Hello.
Hello again, louder. You took real query load and you reran it against your own test rig. So the packet mix was a direct reflection of a real query load.
Yes, a 10-minute sample.
Right. So that's good because there's the confidence component. This is a reflection of real traffic mix as seen really at a real root instance, diverse, the qualities of why you see the short and the long query mix. That's what the world does in that 10-minute sample. This I like.
Right.
The CDFs of the old 512 versus the rest, there's a thing in my mind thinking those 512s are the ones which are least likely to ever get fixed because they're the intractable cases that are stuck behind something that's not going to get upgraded. So the quality of that curve, the red part, is the lingering hell that we're left with. But your blue line is saying, yeah, but it doesn't alter the trajectory overall of the real world. They happen to be a particular set of their own, set against the volume of people who can handle larger things. It actually has a less effect. Is that kind of what you're saying?
Well, the red line, in this case, we're not particularly worried about because these are not asking for DNSSEC.
Right, they never do it,
Right.
Except for, well, let's go with they don't do it, so you don't see them as a tractable part of the problem in that sense.
But yeah, you're right that they're behind the curve and getting upgraded.
So if you roll forward about 5 and you get to the one where you show the TC figures,
This
again,
one?
and more.
Oh, the bar charts? Like this?
I think it was back one. No, back forward. Yeah, it is only a small percent, but it's 4 times the current TCP load.
Well, this is for DNS key responses, DNS key queries only.
So it's not the total consequence of increase in TCP, it's the amount who shifted to TCP specifically doing DNS key fetches.
That's for DNS key. This one is for all. So here it's about a 3x increase in TCP.
So you've got a plan for 3 times the TCP load that you're currently syncing.
Right. But which is still quite low. I mean,
Right. So for you, it's under the capacity planning limits that you would have naturally built in anyway with growth in service.
yeah, it's like going from 1% of every less than 1% of every UDP query would be TCP to it's this.
Yeah. Okay.
So
Thanks. I'm just checking my understanding.
in terms of absolute, it's still a pretty small amount of TCP, I think.
Okay.
Yeah.
Peter Gordinik. Dwayne, can you go to one of the slides where you show these invisible fragmentation at the end of the presentation? Yeah. So is it that you're only taking into account, no, you're taking into account all the queries that were sent regardless of DO bit, right?
Right.
So this is all from the perspective of the serving root server and the load and the effects on that side. Where is...
So to be clear, this was, so I didn't actually, run PCAP and look for fragments in the PCAPs or anything like that. This is sort of predicted fragmentation based on the size of the response, right? So
understood.
Yeah.
So there would be 2 questions from that. Is that consistent with the amount of fragmentation that you see in real life on your root name servers? i.e., is there any other reason to fragment rather than hitting the 15.0 boundary?
So it's a little bit tricky for me to answer that because our servers, VeriSign servers, are actually configured to not fragment.
Okay.
So we will truncate before fragmenting.
Okay, fine. So the response is yes, but probably for a particular reason that is configured in. The other question I have is, again, this is the perspective of root server operator, which is perfectly fine for that presentation. Now, to complete the picture, wouldn't we need something, another study maybe, that focuses on the desperate resolver who is now told, well, maybe you are unlucky, but there are so many million other people there that you're somewhere in the white noise. And if we strive to increase the deployment of DNSSEC, the people being pointed to the white noise that the others generate aren't really helped with. And more importantly, if the DNS key queries turn out to be crucial and they're still in the white noise, they might be the roadblock to further developments here. So I'm wondering what you envision as the complementary study from the recursive side.
Well, I would say that the work that Jeff is doing, that Jeff and George are that complement to looking at the recursive side, to looking at the client side. And I think Jeff can maybe have a few things to say about that.
Jeff Houston, APNIC. Yeah, we have been doing some work recently. The bit that sort of what you're saying is as long as you sit under 1500 octets in the response, V4 is kind of fine because unless there's just violent aberrant crap going on, the response will go out as a single UDP response and you're just fine.
Right.
V6 is bizarre. And in particular, you might have a very high EDNS0 buffer size, but I've certainly noticed resolver behaviors, and Bind has this, of setting your socket MTU at 1280.
Right.
And as soon as you exceed 1280, you're below EDNS0 of the client, but you're going to frag the UDP response. And that becomes the issue. And then the question is, how many V6 queries exist in the world today? And the answer is certainly not zero. It's not really high, which is its own question. But there's enough to go, we are going to see frags in V6 because the client is going, I can do this. And if you're running a 1280 MTU socket size, you run into these problems. Now, you might not be doing that in your resolvers, and that's brilliant. I don't know what the rest of the root server name set do. I've no idea. But, apocryphally, I've heard some of them did set it at 1280. I haven't looked. And that interaction might be a bit tricky because if they're going to frag anything, V6 is the world's worst protocol to frag.
Yeah. And I think that the only sort of comfort there is that, we can probably, at least for a while, we can assume that if you're having trouble over V6, you have a better path over V4 to retry, right?
There's always dual stack, and that'll
so-
hold for at least another month.
Yeah, you're not gonna be dead in the water at least for another month.
Yeah, right.
All right, thank you.
Thank you, Brian.
All right, and the next talk up will be Oliver Gunnarsson. Philippe will be up, and he's going to be talking about live signing on the fly.
Mind if I plug a speaker?
No,
All right.
just double check that it actually.
If it doesn't work, we can just drop it. Close it. Yeah. No, you can.
Oh, it doesn't even care, right?
Yeah. All right. Hello, everybody. As many might have noticed, the Cloudflare is starting to do DNSSEC, and I've been working on implementing DNSSEC on our server. I will keep this nice and short and speak about technically how we're doing it and what we'd like to see happen. First of all, I have to tell you why Cloudflare needs live signing, because obviously there were good tools to offline sign your zone. That was already done. That was easy. That was possible. But the problem is that Cloudflare doesn't really have a regular DNS infrastructure. We have a really distributed network with many small zones that don't see that much traffic. That don't all see that much traffic. We have really hot zones and really cold zones. So it would be obviously a waste to sign everything all over in a centralized place and then ship it to the edges, or sign on every edge, every record, every time. Same reason. Well, same point. We have a really distributed network. We would have to decide whether to sign centrally, keep the keys safe, not on the edges, and then ship all those signatures to all the edges with all the replication problems every time the R6 expire. Or we sign on the edges. We keep all the keys. We keep the zone signing keys on the edges, which is acceptable, but still we would have to make the signatures 34 times over. But even more interesting, Cloudflare does actual business logic in the DNS. We route traffic to our CDN or directly to the client. We do CDN flattening. We do many different things that are dynamic. We don't really know what we will answer before we do. Or it would be a real waste to go ahead and pre-compute everything just to sign it, just in case we have to send that. And finally, zone walking protection. NSEC 3 is not really for confidentiality, I'm sorry. And NSEC 5 looks really nice, but it's not here yet. Validators are not doing NSEC 5, so that's not an option. So, live signing. Live signing, easier said than done. We have three main problems. Live signing requires CPU speed. At Cloudflare, we have a single server that does everything. A single server, yeah. We have a single server type that serves HTTP that does everything. That's what keeps us flexible, because we can spin up as many servers as we need with traffic. But it also means that if I eat all the CPU to do DNSSEC signing, the other teams will not be happy. Then, negative answers. Negative answers are really big, and they would require many signatures, and again, CPU and size. And finally, key management. It's not offline signing. We can guard the keys, use them only when they're needed, and then tuck them away and make sure that we don't touch them in the same machine as traffic. And finally, we have to keep some constraints in mind. Keep the size small, because at Cloudflare, obviously, we're a hot target for reflection attacks, and we can't really go out and start sending 2K UDP packets. And we don't want to require full zone files. That's another peculiarity of how we do DNS at Cloudflare. We don't have zone files replicated to all the edges that are loaded into our server. We have a distributed database that holds all the records separately, because after all, we usually don't see a whole zone asked at the same time. But usually we see single records. So we have a database which is flat, and we just pick the record we need out. So our solutions, how we are doing it. First, a quick overview of our server works, just as an introduction. Our server is called RDNS. It's written in Go. It does everything as a series of filters. Think it as operations that are done on a query when it comes in and on the answer as it grows. So we take something out of the database, we do the dynamic interpretation, we do generate the dynamic answers, and finally, DNSSEC. DNSSEC has to fit as another filter, another step in this process that takes an answer that is ready to ship to the client, tuck a signature on it, and send it. As I said, we have no zone files. Everything is pulled from this global distributed database. So if we want to go pull everything else that is in the zone, that will be many other queries to the database and slow down. It's pretty resilient against attacks and abuse, even if it doesn't do the volumetric side of protection, as you heard yesterday, but it's still geared to protect our customers, our origin IPs and backends. Finally, it's full-featured. As I said, there are many filters. It doesn't just pull things out of the database. It does a list of operations on it, and different teams insert different filters. So DNSSEC can't really go tell all the other filters what they can or cannot do. First, solving speed. Making up to 3 RSA signatures every time we answer a query is not really an option. So we turned to ECDSA, not just for that, also for size. But we still found that ECDSA in Go was slow. It was implemented natively in Go. As I said, our server is written in Go. That's great. That makes development really easy, really fast. But the crypto library wasn't up to speed yet. So Vlad Krasnov is part of the Cloudflare team. He's the person that wrote the ECDSA P256 implementation of OpenSSL. He turned at Go and he ported the OpenSSL implementation. I keep saying that Vlad is magic because we got 21 times speed up on ECDSA signatures. I was worried that, yeah, I have to rate limit and I have to be careful with what I do. If an attack hits, I don't want to waste CPU. Then Vlad came, and now it's basically as fast as pulling stuff out of the database. I don't even see the signature time, for one signature at least. Here are some numbers. What signing with ECDSA was before and what after. While we were at it, we also optimized RSA. There's a blog post. Also, size. RSA 1000 is not an option. We are fighting to get it out of TLS. We are starting with a new DNSSEC stack. We don't want to go ahead and implement RSA 1024 in our DNSSEC. So here is the comparison between RSA 2048 and ECDSA 256. The second will fit the 512, will work with any server you have deployed. The first one, well, it's something like 50 times reflection potential. Also, I'm a bit disappointed that no one noticed a little Easter egg here. have you ever looked at our key tags? At least the one for my zone and the key tag of the zone signing key. The one of the zone signing key is a bit more obscure, but this one should be a reference. Anyway, you can look it up later. Finally, speaking about ECDSA, you already heard from the talk before me how deployment is going, how validators treat ECDSA. So I'm not going to tell you much about that, except that DNS OARC network, the Wi-Fi network, doesn't validate ECDSA. People, no. Anyway, what's more interesting to talk about is registrars and registries support. We found out when trying to put up Cloudflare auth demo domains that we couldn't use our main registrar. Most of the other registrars we checked, the DS record with algorithm 13, ECDSA P256, was supported basically nowhere at the time. Now things are catching up. I think that GoDaddy is on board finally, but it's surprising also how many registries don't don't accept. It's a matter of accepting, not actually, implementing ECDSA. Just don't accept the number 13 in that field. So please help us. We need to get everyone on board with this. Okay, so on to the more interesting stuff. Black lies. The problem we are trying to solve is that to make a negative answer by default, vanilla, a normal negative answer can take 2 or 3 signatures, depending whether you do NSEC or NSEC3. So it's slow, twice as slow, thrice as slow, and it's big. It means sending twice the size of the packet, 2 NSEC, 3 signatures with the SOA. No matter that we are using ECDSA and going all the trouble to get ECDSA working in the world, and then we are going back with negative answers like that. And it needs a database lookup for the previous and next name. As I told you, we don't have a zone file. We don't have the full view of the zone file when we create our answer. So we would have to go ask the database to do a prefix search or a sorted search just to figure out the next and the previous. It's just, that would be just crazy. And finally, we disclose the previous and next name. That for some customers is not that important, for others is. See, 736. That might seem small, but for my target when I started was 512 or bust, because that's how we avoid killing other people on the internet with reflection. We decided that we are not sending UDP packets bigger than 512, and it's working. And we don't see that much truncation unless I start doing basically this. One step in the right direction, RFC 4470, white lies. White lies are a great idea. They say, well, if you're live signing, you have capabilities, so let's use it. Let's simply, instead of going to the database, figuring out the previous and the next name, just take the predecessor, the successor, and RFC 4471 will even tell you how to do it. If you're doing it with NSEC3, it's even easier. That will cover the name, but you still have to make a wildcard proof because the NSEC is not on the name. So you have to prove that the name is covered by NSEC and that the wildcard is covered. So we still have 2 signatures, 2 NSEC, and we have 2 signatures operations. Solves zone walking, solves database lookups. Still, we can do better. We can just lie. They are called white lies. Let's go all the way. This, by the way, is DNS reactions. It's pretty popular at Cloudflare. I don't know if you follow it, but it's fun. The idea is just sign a no error. We want to send out the concept that the name does not exist. Well, that requires at least 2 signatures. We tried other solutions. There are some solutions using NSEC3 that might be standard compliant, but they don't really work with implementations. This happened a lot during this process. Things that would work with implementations were totally not standard, and things that were standard totally didn't work with implementations. So it's striking a balance, making everyone happy. So to realize, make an NSEC record, put it on the name, cover until the successor, and set only NSEC and RSEC bits. By the way, the white lies RSC allows us to set just those bits. So here it was 3. This turned out to be a problem for some validators. I honestly didn't pick 0 because I thought, oh boy, 0 is going to break so much software. And I broke software with 3. So yeah, I just reverted to 0, and I'm just following RFC 4471 now. It's a valid character. We did it. It's 363 bytes to send a negative answer. A full NX domain, including SOA, NSEC, RSEC on the NSEC, RSEC on the SOA. We're fitting the 512. We don't have to worry about fragmentation, about TC, about anything. Finally, 1 signature operation, no database lookups. We don't even need to know we don't even need a database connection. And there is no zone working. Finally, the end user behavior, what matters to us, is completely unchanged. The user went in their browser or in their application, tried to look up the name, and it got a negative. True, the resolver knows that it's a negative type, not a negative negative name answer, but still, the end result is the same. To help the resolvers, we are suggesting to define an NSEC bit that means we actually meant an X domain. So if you want to go ahead and cache the fact that there is nothing below here for key minimization, this bit tells you that, okay, please go ahead. This was meant to be an X domain. There is a draft. It's my first internet draft. Be kind. Okay? I mean, if you have to complain to Olafur. There's his name too. Anyway, this what we suggest. If anyone has better ideas, we are still in the process with this. The end user experience is already working. Now, on to something I find even more fun. What I call the NSEC shotgun. We still had a problem. We solved the more nasty ones, the NX domains. We made them small. But also the actual no errors. When you ask for a type and we don't have that type, those were kind of tricky because, again, we don't have visibility into the database. And we need to know all the types that exist on the name just to tell you that that type does not exist. Keep in mind that this for Cloudflare was not even always possible. We had to basically guess because some records are generated on the fly. So we would either have to go ahead and generate all the possible record types that might require going to the network, doing complex stuff just to throw away what we generated and keep only the fact that a record ended up existing or didn't, just to set a bit in the NSEC that the end user doesn't really care about. They care about getting the information that the type they asked for doesn't exist securely, right? Now, to solve this, we took a step back. What's an NSEC? An NSEC is a list of types that exist. Okay, I get that. But that's just the semantic, how it appears. But the meaning of an NSEC is actually a denial of existence. So what actually matters in the NSEC is the missing types. A NSEC is a statement that says these types do not exist. It's done by saying which ones exist so that offline signing is possible. But we are live signing. We don't actually care about that. We only care about not allowing the attacker to replay this packet, right? So what we did is making a manually covering one by setting everything. That's minimally covering because, as I said, NSEC is a statement of a denial of existence. So if we don't deny almost anything, we are covering only the type we were asked for. So you ask for TXT, okay? We want to convey the information that TXT does not exist, convey it securely, and make sure that the attacker can't use that packet to go ahead and say that A does not exist. That's the point of NSEC, right? So you ask for TXT. We take all the possible types that we can generate, proxy, store, set, will set in the future, whatever. They're cheap, they're 1 bit each, 1 byte every 8. If we don't start setting them like one distant from each other, it's gonna be fine. And we remove TXT and send that. So you ask for TXT, I'm sorry, all the types exist except TXT. Really, that's unlucky. Then you wait some time and you come back and you're like, okay, give me a MX. And now we send ANS, SOA, HINFO, TXT, AAA, etc. We tell you that everything exists, TXT too, but MX doesn't, sorry. So is this standard compliant? Yeah, in the gap between your two answers, if you want to think about it that way, the TXT might have appeared and the MX might have disappeared. So that's for standard compliance. Does this work? Yes, it actually works. So, and finally, can an attacker use this to build an attack to say something that it's not supposed to say? No, because we just sent a packet that can be used to negate the existence of TXT. So if you try to send this packet to negate the existence of anything else, to say anything false, it's gonna fail validation. So it works, it's secure, and we don't need to know what types exist on the zone anymore. We can go completely blind on the database, don't do any lookups, and just sign stuff securely on the fly. Finally, a quick word about centralized DNS key set. Obviously, we still need to sign our DNS key RR sets. So the keys key is clearly more valuable than the zone signing key because we can unilaterally roll the zone signing key, but not the key signing key without the help of the user setting the DS record, at least for now. So what we're doing is that we are keeping the key signing key in a secure machine centrally, signing all the DNS key RR sets periodically, shipping them and only them to the edges, which is not much, 1 signature for every zone every 15 days or something like that. It's reasonable. And then we keep the live zone signing key in memory in the database, ready to make the signatures. And finally, we talked about how to generate keys. And if you think about it, all our zone signing keys would have to be live on the same server at the same time, because we need to sign all our zones from all the machines. And all our key signing keys would have to be live on the same secure machine because we sign all our zones. So it wouldn't really have any boundary. So why use different keys? We're just reusing the same key for all the zone signing keys, and you're reusing the same key for all the key signing key. So the beta is different. But this is still secure because the signer name is in the RSIG, it's signed, but allows us to control and guard a single key, which is reasonable. Someone asked me, but what if a customer comes and tells you that their zone signing key, they think it's compromised? Well, if I store that next to all the other zone signing keys, I'm not going to roll his zone signing key to make that customer happy and then go ahead and live happily. If the attacker got their hands on one zone signing key, they got them all. So I'm rolling them all, which is harder than just regenerating a single one. So this is actually a better solution, even in that case. All right, so this is it. Takeaways: we set all the NSEC bits. we do horrible black lies, but we want to actually tell you with a NSEC bit that we're doing it, so that we're square. And there is something hidden in the key tag, and that's basically it. Questions? By the way, yeah. For those in the back of the room that can read it, this is DNS reactions. What an engineer at Cloudflare must feel like. I've done stuff I ain't proud of, and the stuff I'm proud of is disgusting. That's basically me, I guess.
Hi, Matthijs, Dijn. Thank you for a very nice presentation. I was just in time. Two things. You want to suggest an R type, or Oliver wants to suggest an R type for signaling NX domain. I wonder if you need an NX domain, a new R type for that, or you can do something like we did for NSEC 4, which was a sort of a research experiment. You have a lot of bit flags there you still can use. So that might be something to look into. And the other thing I wonder is a question, actually. You mentioned some measurements about ECDSA signing speed. I wonder, did you also test or measure the validation speed?
Yeah, I knew this was coming. ECDSA validation is slightly slower than RSA validation. Keep in mind that I'm always comparing RSA 2048 because I'm not even considering it RSA 1024. Yeah, it's slightly slower, but I feel like we are probably concentrating in the same place more signatures than verifications are concentrated in the same place. I may be wrong. If resolvers start suffering on the CPU side because of this, I'd be happy to talk. But I think that considering that we are reducing the CPU load of negative answers by threefold, up to threefolds, I'm not really sure our authoritative server will put more CPU strain on resolvers than others. Because that's part of the reason we worked on reducing the number of signatures. That also reduces the number of verifications you have to do.
Right. So, but you do have the numbers, and this is something that is being sort of mumbling in the hallways, like it's slower. And it would be really nice to see these numbers. And if it's not that bad, maybe it's worth it.
Yeah, the numbers are actually pretty easy to figure out for OpenSSL, for example. You type OpenSSL speed, RSA 2048, and ECDSA P. No, 256K. It's in the man page, but still. But the numbers I don't really have is how many negative answers are get verification as opposed to how many positives. That's what I think will put us like will make a trade-off with the speed. The single signature verification will be slower for the recursor, but my theory is that they will have to make fewer of them.
Okay, thank you.
Hopefully. And thanks for the suggestion.
Ed Lewis. So yesterday, the first talk by Fujiwara-san talked about having resolvers take on more of the authoritative recursive servers take on authoritative server functions by using the NX domain or using the negative answers to expand what they could do. And that was, at the time, it was questionable because we don't really want to have the recursive servers taking on what the authoritative servers are responsible for. But what he was saying makes sense. You know, I've already told you it's not here. Now today, your presentation has a way of changing negative answers to make it easier on the authoritative side by telling the recursive server less information, right? Right.
Yeah, I mean, we do give the recursor less information for the zone actually existing type does not exist case, where you can't just decide not to do the lookup of the A because it's not set in the bitmap you got from asking for a MX.
Yeah, I was going to say, just be cautious here because, you know, and this is not just, I'm not picking on your this proposal, but in general, I see this, and I said this to someone in the hallway yesterday after the first 3 presentations. Everyone comes up here, here's what I want to fix, and here's a way to fix it. And that's fine. That's fine. That's acceptable. Everyone does that. You go out and say, here's what my problem is, and that's good because that's what we really want to solve. And here's a way to fix this. But we have to keep in mind now that we're going to have to make sure that all of these fixes aren't dancing around and getting people in circles.
That's the point of the NX domain type bit in or flag in the NSEC anyway. That would communicate.
Right. 'Cause I was imagining when you're doing that, if I were the receiver of that, I might get confused saying, well, you just told me this and told me that. And I may, who knows what the recursive server is going to implement? Are they going to go back and retry, you know? So I'm just pointing out, this is not necessarily saying it's a bad idea, but we have to integrate all of these little fixes that were being presented here in this meeting to make sure we push as someone say, push the burden around correctly.
I gathered that.
Ed.
Yeah, no one meet later outside in the bar, yeah.
Okay. The answer to this question is twofold. One is, this is where we took the envelope as far as we could in making things small. If under certain circumstances, and if our customers allow it, we could return NSEC records that are just like normal ones. So like if we have a domain that is under attack, we can change our systems to give out a wider NSEC records. That would help resolvers. Okay, we haven't done that work yet, but it is something we have thought about.
Again, the semantic of NSEC help here because we could do the two things at the same time. So send one with all the bits set for regular traffic, and resolvers don't need to special case that. They would just have to do the follow-up query. And then we can start dropping bits when we are under attack, and the resolvers can just use that information.
Hi, Roy Arends from Nominet. None of the stuff that I've seen here is actually new. We've discussed it in various groups, and we sat around tables and beers and dreamt of hacks like this. And hacks, sorry. And I must say, I love it. What I'm really, really, really impressed by, and what I think is really, really good, that you're actually betting the company on this stuff. Right? You're doing this in production. You're willing to do this in production. You do this with fairly controversial ideas. I know they work. I've tested them myself a long time ago, but just discarded them because I didn't want to have to go through the pain again of changing a protocol yet over and over again, because whatever idea that we had at the time, we just had finished DNSSEC standardization. So I completely agree that, well, I think a no data or an empty non-terminal, that kind of response, basically a no error and a no answer, that to me is a subset of NX domain. So you're doing it the right way around. So fine, that's absolutely fine. Of course, you know that if you do the other way around, if you're going to rewrite a no data with an NX domain, you'll be in trouble, but you're not doing that. So I absolutely like it. I think we had a discussion at one point in time, I think it was over video. I'm not sure, it was quite recently, maybe about 4 or 5 weeks ago or 2 months ago, where I tried to explain an alternative, the NSEC 3. You mentioned NSEC 3 here. I'd love to sit down with you and Oliver and have a small discussion on why you haven't chosen for NSEC 3.
We'd be happy to, because we did the idea seemed as viable as using NSEC, but then we did test it, and I think Unbound or other implementations weren't really happy about doing it with NSEC 3. It would be probably nicer because finding the successor of a name for NSEC is a easy case, and then a lot of special cases with the maximum length and number of labels, etc. But yeah, I'm aware that black lives were considered in other places.
Harmless.
I was not. I didn't know that anyone else thought about the shotgun. What they call the shotgun. Anyway.
Yeah. To be fair, you're right. The shotgun idea, the idea that was presented in the past is having type any, right? That is I think that's RR type 255.
Mm-hmm.
When that is present in an NSEC type bitmap. Thank you. When that was present in NSEC type bitmap, it basically means, yeah, everything exists except what you're asking, which is not really true. So we discarded that idea. But actually just enumerating all the types that could exist,
Yeah,
except for the one that you're asking for, hey, that works.
What the query type is not signed in an NSEC, so that opens to a replay attack, doesn't it?
Sorry, the Q type is signed in NSEC.
The query type, the one that was queried for. Query
Oh, the
type.
query type.
Sorry, yeah.
Well, if it doesn't exist, there's nothing to sign. So you need to make a statement about its existence, which is the NSEC record. And of course, the type bitmap is part of that record, and you sign the entire record as a blob. I'm not sure if that's what you meant. But
Anyway, we can talk about it
yeah,
later.
let's have a beer. Yeah, brilliant stuff. Thank you.
Thank you.
Over to Peter.
Peter Kortinik. Like Roy, I wonder a bit why we put so much effort in the design of NSEC and NSEC3 and so on and so forth, and try to maintain semantic consistency of the protocol, but that were different times. So that said, you might take the following suggestion with a grain of salt. You said that you enumerate all the other types in that bitmap. That would probably give you a 64K bitmap, and you don't. So you optimize and you take one of the slices there. Why not get a step ahead and get rid of the whole bitmap? And so deny the existence of any type. So we didn't do that at the discussion of NSEC because that had this silly NSEC bit, the NSEC denying its own existence and so on and so forth. But that doesn't matter anyway in that scenario.
I'm a bit confused because this seems this similar suggestion at least as the previous one. But what I don't understand is that when we answer for txt, we set all the bits except txt, and that's what tells the user in a signed statement which is the type that does not exist. If we just set any bit, can't that packet just be replayed to deny the existence of any type?
Well, what you do is you set all the bits in the first slice, so that you deny the first 2056 record types. Now, if there's a record type...
No. We set all the possible ones. Allocated in use. I mean, all the ones that anyone would be actually willing to send. And if someone standardizes, allocates a new one, we will add that because it's not forever. It has a validity, right? The signature. So we can just add another bit in the system. If you find a type that you want to ever send that is not in our slice, please let us know and we'll flag it. But we are hoping that, let's say, the working groups will not standardize 60 or 100 types before we move on to something else. I think that might be a safe assumption.
Well, so the assignment policy is, that's an interesting challenge because getting RR types should be easy these days. Yeah. That's an interesting challenge, convincing Ayana to give me a type in either slice. But that, no, seriously, that means that whenever the allocated, the list of allocated RR types goes beyond 256, and actually we do have something beyond that, but I don't remember off the top of my head, you need to change your assigning policy. Good luck. Thank you.
Well, it's a line in the code, but thank you. All right. Thank you, everyone.
All right. And right before we go on break, is Matt Pouncett around? Yeah.
Yeah, so just a couple of quick notes about the PGP key signing. So we're going to be doing that at 1 o'clock in, I think it's called the Meerman Room. Is that right? Is that the right name of the room? Yeah, just across from the elevators. So I sent out an email to the attendees list a little while ago, just with reminder information about that. So please send keys to the email address I sent there at pgpsign@dnsoarc.net. If you're using an older key, now would be a good time to sort of update to a stronger key. Any 1024-bit keys are sort of considered to be not secure for the average lifetime of a PGP key. So you'll probably want to update those. There's a link in that email that kind of talks about that a little bit. Please bring ID that matches the identities on your keys. Other than that, I think that's, unless anyone has any questions about it. All right.
All right, and if everybody could get back here at 10 to 11. Break is right next door. Thank you.
Okay, I will now hand you over to the chair for next session, which is Sean Stewart.
Morning. Our first presentation this round is a day in the life of a DNS resolver with Mr. Bruce Van Nies.
Work for Nominum. We've talked at a lot of these conferences, and there's been a real heavy emphasis on security, specifically all the DDoS stuff that has been central to the conference so far. Today, I thought I'd just take a different tack, and we took on this project to go look at resolver data, specifically as the title suggests, go grab data from a single resolver for one day. So I did this in conjunction with one of my colleagues, Yuri Yuzifovich. Yuri actually was supposed to be here. He's having trouble getting a visa, so hopefully he'll be able to make the next conference, because he's the guy that actually does the intensive data work to derive the charts that you'll see today. So we took 24 hours of traffic from a European resolver. This is a provider that is primarily consumer broadband. Just as an aside, to offer a little perspective, there's some attack data that we have, and just to give a sense of how that could have been, this particular provider has one open DNS resolver per 200 users approximately. So that's the vector that's used for some of these attacks, and I just wanted to give a sense of the scale of the exposure that they have. The data that I'll show today is mostly covering incoming queries. We do have some response data from attacks. We can collect both. Our servers are well instrumented, and it doesn't stress them to collect the data. It just becomes a practical issue of how much customers are willing to gather and aggregate and ship off to us, and all the logistics behind that. So just from this project, we've realized that getting more response data is useful for a lot of other things, and so we'll going forward, probably do more of that. One of the other things that we did is we matched the data that that I'll show against threat lists that we have. Our primary reason for collecting data is to generate threat lists, specifically for DDoS and for bots and other kinds of malware. So that's why we gather the data, and out of that, it's actually a product that we sell. We offer to our customers because they can use that to protect their resolvers with various filtering capabilities. So our focus there is all the DDoS, all the variants, and all the the evolution of DDoS that we've seen over the past couple of years, and then bot activity. So this proved to be a really interesting project. Day to day, our production network is set up for dealing with aggregate data, and so there were some unique challenges just getting some practical issues with getting data from a single resolver. So I think it'd be fair to say we endured a certain amount of stress. It was intensified because we also moved our corporate headquarters very recently. So in the midst of this project, the production network rightfully took priority, and a science project that we were doing didn't, and so things getting taken down and put back together introduced some other really interesting dynamics. So one of the things we did is we initially filtered for most active domains. We drew like 24-hour charts of hourly queries for a bunch of different kinds of data that was DDoS related. We looked for known malicious domains matched against the list that we have. We looked at different query types, and we looked at some flags, and I'll show you what all that is in a minute. We, in some cases, did some secondary filtering. Since we have access to all this data, we figured it might be interesting to look at it in a new way. We tended to look at data like on an hourly basis. So for example, queries hourly. And we thought it might be fun to see what happens when you look with much more granularity. So I'll show you some of those charts as well. So this was the 24-hour trend. This is just queries per hour, and this is usually what you see when you look at resolvers. We look at lots of them, and I guess one thing you'll notice right away, as I said, it's consumer broadband. It must be a pretty diligent group of people, because there's that nice spike first thing in the morning. Everyone's hard at work already, trending all the way through middle to late evening, and then down the diurnal trend we always see at night, down to a trough in the very early hours when there's not much going on, at least not much human generated traffic. There's usually a lot of machine generated traffic. So in terms of the IP counts that we saw on this server, you'll see they peaked at around 80,000 unique IPs, and the low was around 68,000. Obviously, you know, stuff's connected all the time, so we see queries day and night, and you know, even home gateways and other kinds of things are querying for various reasons. So there's some fluctuation in the IP counts, but 80,000 is probably on the low side for what we see on most of our servers. By the way, I didn't say when I put this slide up, this server too at 5,000 QPS is far from being stressed. I think most of the servers that we deal with run many times hotter than that. This server did about 422 million queries that day, which also is pretty low, maybe an order of magnitude below what we often see for a production server at a provider. So one of the things we looked at were the top 10 domains queried per hour, each hour. So this is the best thing we could come up with. We're actually hoping to have better data visualizations. It's kind of an interesting problem, you know, how you graph stuff. When you have something that can change hour by hour, you'll see some of the domains tended to persist over the entire 24 hours. They made the top 10. Some didn't. So there was more than 10 over the course of 24 hours that made the top 10 in any given hour. This is also data that used an inexact match. So if you look at what the domains actually were, you'll see that any domain that contained these rightmost labels was tabulated for what you saw in the previous chart. And if you look at this, you'll see, you know, most of these are pretty familiar. It's more or less what you'd expect. What are there, maybe 25 or 30 of them? So you know, all the sort of common consumer names that you see on the internet, Belkin's out there, they've been a problem. And this too is what we normally see. I'll talk a little bit now about matching against the threat lists. I just gave a little perspective on, you know, what sort of the normal activity is. We build threat lists based on worldwide provider data. So we get data shipped in basically in real time every day, 24/7. So that's one of the things that we use to build our threat lists. We process that data in various ways. In fact, we compare against other lists and other sources of security data. And other network data that we have access to. We have a whole data warehouse that we built that allows us to do this in a very efficient way. One of the other things that we do is we take, you know, what we believe to be suspect threats, and we do very extensive validation. Since we have a commercial threat list, one of the things that's really critical is that there are no false positives, since that can cause problems for our customer base. If they're inadvertently blocking traffic that's legitimate, usually that's something that precipitates like a support call because someone can't navigate somewhere that they want to go. So we have a whole validation process that we undertake. In fact, that actually takes far longer than processing to find the suspect threats. In some cases, depending on you know, what happens during the automated checks, records get kicked up for a manual check as well. Again, just to prevent any kind of false positives. So it's just to give you a little sense of, you know, how we derive the lists that I'll then show that we use to match against. One of the things that we've been very actively pursuing are the random subdomains. So Ralph talked yesterday about that, and that obviously it's a problem that's been central to this conference probably for at least a year. This is data for the resolver that you just saw, and it's the same scale as the other normal traffic, just to give you a sense, relatively speaking or visually, how much of the random subdomain activity this particular resolver was seeing. You probably recall the curve that you saw at the beginning, looked about like that. And so the random subdomain activity is, throughout the course of the day, less than 5 million queries per hour. There were two, in this case, domains that were attacked. This 888FY and www.bet16.com. And you'll see the attack lasted, actually this is a little longer than normal, probably 14 to 16 hours. And that the level of activity was fairly constant throughout the day. As I said, one of the things we wanted to do is just look at the data basically in high resolution. So this is the start of the first attack, the first blue line. And one of the things you'll notice, and Ralph's talked about this, we think the attackers are getting pretty sophisticated. They have a high degree of control over the infrastructure that they use, and this sort of validates that. You'll see there's just not a lot of variation in terms of the QPS. So at high resolution, you can see the attack starts right up, there's a little bit of a peak and it drops, but there's very little variation. You'll see some lines where it drops. We think that's data that we lost. So there are a few cases where there's some drops because of data loss in all the processing that we do and aggregating and transporting the data. This is a case where we looked at not only request data, but also response data. So once again, it's queries per second, and this is over 6 minutes. And you'll see the same, this is the red attack now. And you'll see, once again, that initial spike, and then you'll see, once again, fairly bounded in terms of the level of queries per second. But the other interesting thing that you'll see here is the impact on the authoritative server. You'll see, sort of that exponential decay, kind of a function where it's clear the authoritative server is, under significant stress, and it, successively answers at a lower and lower rate. So, this is the sort of thing that we can graph in high resolution when we show response data. Just to give a sense of the number of IPs that were involved, in this case, there's actually a big long tail. In this case, I think there were a couple of thousand altogether, most querying at very low rates, but you'll see there were a few that query at very high rates. There is some variability in terms of, what devices are capable of that participate in these attacks. In some cases, they're capable of sustaining several thousand queries per second. In other cases, much less than that. But this just gives you a sense of the distribution of the number of IPs, and then on the left-hand axis, the total queries that were sent by each IP. So you'll see one in particular that was sending more than 120,000 queries over. I apologize for the time frame is the duration of this the second attack. So this just gives you a sense of the scale of, or the number of devices that are participating. As I said, 150 to 200 were active, and then there's a long tail of devices sending at very low rates. One of the other things that we look at is DNS amplification. This was a big deal 2 years ago. DNS amplification was far more common. There was this whole resurgence in DNS DDoS that started in late 2012 with amplification attacks directly on authoritative servers. And that quickly shifted to attacks that are reflection type attacks, which led to the realization that there were all these open resolvers out on the internet. So one of the things we've been tracking for a long time are DNS amplification queries. Some of these will be familiar. They're, as you'll see on the next slide, there are any queries. Some are what we call purpose-built amplification domains. So these are domains that were registered specifically for the purpose of DNS amplification. So we track all that. One thing you'll notice, the level of activity here is far lower than it has been in the past. This, realistically is pretty much noise level for this resolver, for any provider. It's not really a troublesome level of activity. Then, fairly modest number of domains that were used as well. Whoops. This is another one we just ran in high resolution. You'll see the traffic is kind of self-similar. You look at it at different levels of resolution, and it looks very similar to what it did on the previous slide. We did this just because we could. It was just to see, what the graph would look like. So it's the same domains, but just much more granular. You'll see less control over the infrastructure. This is probably not the guys that are doing this for whatever modest amount of money the DDoS for hire services might generate, but people who are just playing around and aren't particularly sophisticated. But again, it's not necessarily traffic that's going to be troublesome just because of the scale. So just a summary of this data relative to what we normally see. As I said, we mostly look at data on a worldwide basis, and so we drilled down and looked at data on a single resolver basis. And so this resolver saw about 12% DDoS traffic, and about 88% was normal or benign traffic. And the averages that we normally see are about 11%. So this is very close to what we typically see. With regard to amplification, we actually normally see a bit more. The split between the random subdomain attacks and the amplification attacks is usually much more noticeable. We usually see about 85% random subdomain. As I said, the activity is shifted that way. And the remainder of 15% is amplification. In this case, it was less than 1% was DNS amplification. And as I said, there's some variability. The same networks aren't attacked in the same way every day. So this was one day. The next day, things could be different. The random subdomain attacks have been fairly consistent. Amplification hasn't. It's been much more haphazard, let's say. So again, just speaks to the sophistication of the people that are doing the random subdomain attacks. So one of the other things that we looked at was any queries. These are also often implicated for DDoS. Well, I apologize. I don't know what happened to the domains. I was editing the slides late last night. I think I may have gotten rid of the legend. But anyway, there were like 20 domains. Some of them appeared on our threat list, some didn't. Not everything makes our threat list. It just depends how much we see of a particular domain or query type and how it's used and the size of the payload or the size of the response. If you query for any, do you get good amplification? If you don't, that's one reason why it may not make our list. One of the other things we hope to do, we didn't get a chance, was to look and see how many of these any queries are potentially legitimate and not being used for amplification. It seems like that's a topic of interest because there's a general consensus that any is something that probably shouldn't exist, and so there's even proposals or I think networks where it's simply just blocked altogether. One of the other things we did is we identified a bot in the network that was doing DDoS, and just for kicks, this was in the middle of the night, we looked at what non-attack domains it was querying. So it's kind of ironic because if you look, you'll see this was a Zixel home gateway, and the queries to the Zixel domain are for some sort of AV update. There are other AV updates that were queried for as well. So it's sort of ironic that this bot-infected device, which is causing trouble, is getting AV updates regularly and apparently blissfully unaware that this thing can do DDoS. So I said one of the other things that we tracked is bots and malware. And so this shows bot activity. Again, the query level is fairly modest, modest percent or so, or actually a bit more than that of the normal or benign traffic. In this case, I had the domains and I was going to show them. Our product managers were a little nervous about me doing that. So if anyone's really interested, I'd be happy to share that information with them, but they just weren't anxious to have them published on a slide that, that has a lot of visibility. So, but you can see, if I recall, there were like 30 bot domains or so that were querying, and that was just the top ones. As with everything, there was a huge long tail of other bots that were querying as well. You can see some are pretty consistent throughout the day. If you just follow the colors from left to right, you'll see some participated throughout the day. Some started and stopped for various reasons. So this is an area we do a ton of research. We've looked at bot activity for many years and published a list of command and control domains and other domains that bots use either to propagate or to get instructions for attacks. So just for fun, we started looking at some of the other query types. We looked at MX. This is back to queries hourly, top 10 domains each hour. So on the next slide, I'll show the domains. I apologize for toggling between the two because I was really challenged when you do top 10 domains each hour. It means you get 40, 50 or more domains. I think for MX, they were like, oh. Well, there were like 50 of them. I'll drop those in. I'll repost my slides. I think I may have taken those down too. But anyway, this, as you'll see, closely follows the pattern that we saw at the very beginning. So people querying for mail servers or other things querying for mail servers closely correspond to the general pattern that we saw at the beginning of the presentation. Some of the other things we looked at are, flags, and so this isn't going to come as a surprise either. We looked at queries with a DO bit set just for fun. Remember, these are coming from clients, and so we didn't expect to see much, and we didn't. 5,000 queries per hour, actually less than 5,000 queries per hour. These were mostly reverse lookups. There was another query for some sort of config server. It actually the query had this huge label, probably a couple hundred characters. And so I think it's probably like something phoning home or something like that. But anyway, you'll see there was a tremendous amount of variation here. Very few of the names that were queried for consistently throughout the day. So there's a lot of variation here. We also looked at queries over TCP. And, again, as you'd expect, there weren't very many. Less than 5,000 over the course of the day. So just a quick summary. Day in the life of a DNS resolver. Normal queries, we saw about 423 million. The random subdomain queries were about 58 million. Amplification queries, a tiny fraction of that, 392,000. And bot and malware queries, 18,000. Any queries were about 116,000. And again, I didn't have a chance to look at those domains and see how much they amplify, but that's at a level that's probably not troublesome. 121,000 MX queries, 102,000 over the course of the day with DO, and 60,000 TCP. So that's all I have. We did this work and see lots of opportunities to do lots of other things. As I said, we don't often look at a single resolver. We mostly look at aggregate data primarily for security purposes. And so there's lots of offshoots, and seems, there's a lot of interest in what resolvers are up to for this conference. So we'll sort of triangulate with that and see if we can create more data. That's all I have. Are there any questions?
Ed Lewis, you said a couple times about the attack traffic, and you had about this too, that it was fairly mild and could be handled. And I'm wondering if that's said in the context of it can be handled and it's mild for this particular resolver or to the intended victim.
For this resolver, you can see the victim, was stressed.
Yeah.
For one of these attacks.
I think it's important to highlight.
Yeah, I apologize. I should have been more clear about that. That's a good point. We maybe are a bit cavalier. Our resolvers are pretty resilient, and there are other capabilities customers can take advantage of to just get rid of this traffic so that it doesn't infect them. Although in that case, when they do employ those techniques Ralph talked about yesterday, ingress filtering, again, matching against the threat list, it's very effective and not only de-stresses our resolver, but de-stresses the rest of the infrastructure, and doesn't enable the attacker by disabling the domain with something like the authoritative rate limiting that was talked about yesterday.
Hi, Roy Adams, Nominet. Can I see the MX slide? The slide with the MX records?
Yeah, I will get the domains. I'll repost these.
That's fine.
It was pretty late when I was editing.
That's absolutely fine. No, sorry, I thought before I was looking at the total volume of MX records, MX queries, but I'm not. I now see it's for the top 10 domains.
This is just top 10 per hour, yes. Okay. So there likely is a long tail too here. I didn't see the whole data set. I just got select data for this presentation. So if you're interested in any of that, I'm happy to provide it to you.
Yeah. The reason I'm asking is because I was surprised that there are not many peaks, and that has to do with if this would be all aggregate data, then I would be surprised by the absence of peaks, and that of course depends on the bucket size that you're sampling. What we see in our data on the authoritative side, and this for .uk, we see when we see spam runs, we see massive spikes, and we also see a trend in malware that is sending the spam. They actually now go so far as to bypass the ISP's resolver. This malware has their own resolver.
Oh, interesting.
And as you know, it is not trivial, not straightforward to just build a resolver. it's fairly complex.
Yeah.
And in order to get it right, to do the whole proper protocol dance, you have to invest a fair amount of time. And of course, if you're writing malware, you don't have that. So when you write your own resolver and implement that in a piece of malware, you have a very nice signature that you can see.
Yeah.
And I think it is, so I know Nominum, but also Damballa, they look at recursive data a lot to assemble that, security data, these domains that have been infected, or these domains that have been part of DGA, et cetera.
Yeah.
And the trend that we're seeing is that it slowly goes to authoritative only as these malware get much more intelligent and bypass the ISP's resolver. So for ISPs in the room, it might be far more interesting to look at the overall pipe and see what DNS data goes to there instead of just your local resolver.
Yeah.
Anyway, thank you.
Yep. Thank you. Any other questions? Great. I apologize. I will get the data reposted, the domains for MX and any, I think it was. I shouldn't have deleted those. Okay, good. Well, thank you.
Thanks, Bruce. Next, we have dissection and observation of traffic at a residential ISP by Mr. Silvadamas. Not that one. Okay.
That's James.
No, that's very true. There it is. And there we go.
So, my name is Joe Adamas. I work at Bond Internet Systems now. Some time ago, in a previous life where I worked at a company that you all know that produced software, ISC, we were wondering, like, we spent a lot of time actually discussing about what authoritative servers do and don't do, and how they react, and what you can do to make them better. And very little time spent speaking about what resolvers do and what they're subject to. And so it was like, what can we do to have a better picture of what the normal resolver is subjected to every day? So then things changed. I went away. I did stuff, but this idea was always in the background. So now I had some time and started looking at a data capture that I got some time ago from a residential ISP over a larger than 24-hour period for two of their resolvers. But I'm going to focus on one of them resolvers for exactly 24 hours. And the idea is not to track botnets or look at very weird things, but rather, where is there room, or can you see any patterns that will help you with the design of a normal resolver for what it mostly does day in, day out? And also, because it's very hard to get access to this data, does it look like what you see at authority servers, or is it a completely different sort of traffic? Getting a hand on this sort of data turned out actually to be most of the challenge. This is data that some ISP's customers send to the ISP, and then you only see a small representation of that going out to the internet. Because it's each individual customer of the ISP that sends this data, it can be used to identify them.
So that immediately raises a lot of alarms there about sharing the data with a third party that is not necessarily involved with there. So that took a little bit of time and a couple of failures at people who said, oh, yes, yes. Particularly the engineering people said, yeah. Oh. But then someone at legal learned about it and it's like, oh, maybe we need to look at it very carefully. But anyway, in the end, I did get the 24-hour period captures and started looking at them. There's a lot more work to be done. So right now, I'm only going to present on the simple observations. So what you see there is what does the sample actually look like over the 24-hour period. Everything I have tried to reduce to queries per second because that's kind of the metric that we are all used to talk about. So there were 2 servers. One of them served a part of the network that suffered a little outage over there, as you can see, very narrow. It's kind of smooth. It has a daily pattern. You can probably figure out where the time zone for this thing is from the low period corresponding to the night. I ended up doing most of the looks at the data for the less spiky server, the one that didn't go through the outage. The 2 curves that closely match each other for the servers, for each of the 2 servers, are the queries and the responses. You always get more queries than you give answers back because some of the answers apparently get lost, even when everything is only within your network. So what does normal traffic look like? Well, most of them, no error. Thankfully, the internet works. I was surprised about the amount of packets that actually get sent back the refused R code. And looking a little bit more about this, it basically boils down to lots of crappy embedded equipment that send packets out on port 53 or with a destination of port 53, but are not necessarily always DNS. So I guess first rule of a DNS server, cope with whatever is sent at you. There's one very interesting one is there's some intrusion detection software that sends packet out with the ASCII text of the event. So like client machine ta saw port scan on port ta at this time with this MAC address and so on, and sends that directly to the ISP's resolver. It's like what you are trying to do, I don't really know, but you're leaking information like there's no tomorrow, basically. Okay, then you look at domains. These captures come in 15-minute files. So for each of them, I picked the 50 top most used domains and then combine the whole thing, yielding 77 different domains. So for each 15-minute period, I look at the 50 top most, and throughout the day, you only add up to 77. So the popular domains basically are popular all the time and remain so throughout the day. There are, of course, peaks, and everyone seems to be talking about bulking, but what about Netgear? These peaks, orange peaks there, are Netgear equipment trying to fetch something from the network. And when they do it, they dwarf everything else. So because this graph is a little bit crowded, let's look at it from different perspectives. So there you have the Netgear blips, and then even though you clean up things, you still find it hard to see what everything else is. So if we shave off the peaks, you'll find interesting, sometimes I would say surprising domains amongst the most used. You find here and there queries to NTP, but you also find queries to ISC.org. I mean, ISC's software is used everywhere, but why do people keep asking for things at ISC.org? Well, some of the hate actually has to do with dlv.isc.org. The domain that will never die. But then there were weird things that were harder to explain, like RIPE. What the hell is RIPE doing there? And this is a sample from North America, by the way. And of course, the always present HP printers. There were a fair number of queries for rootservers.net and the root zone. My guess, I haven't had the chance to look at exactly which clients source these queries, is that the ISP is mostly residential, but actually has some business customers, and that these business customers run their own resolvers. And that's where these queries come from. So from looking at domains, you can get different pictures, which are the CDNs that are mostly used. Akamai seems to be winning it all. iCloud is so little used as it was at the time of this sample that sometimes it even goes to 0. Ad servers, double-click wins, clearly, but then there are some surprise ones there. Entertainment sites. Well, by and far, YouTube is the most popular delivery network for entertainment. And that pic there, that's what the viral YouTube video looks like. Suddenly, it's all the network sees, and then everyone else moves to the next cat. Stuff that should never be out there, local and .home, wpad.home. Very spiky, but kind of almost constant on the other hand. Leaks. Security services, who is using what? Well, Kaspersky, Trend Micro, of course, the usual ones, the ones you'd expect. Social networks, Facebook for the win. Again, you see the viral spikes there, a little bit broader than in interest than what you see on YouTube. And main site domains, just going through this kind of quickly. Google is the most used website in general. I've included both the Google.com and the Google for the specific country this ISP is in. And everyone seems to prefer the generic over the country, even if Google tries to always redirect you to the country, to the local website whenever you go into a different country. No one actually seems to use that much from what we see. Coming back to more to the part that we like, usage of EDNS from end customers, stub resolvers and on end machines. Not much, to be honest. There's a little bit, but the vast majority of the clients do not even know what that means. Of those that use DNS, how many of them actually set the do bit? So the purple line is the list of the graph of everyone who is actually setting EDNS, saying they understand EDNS, sending the opt record. And the green one is the list of people who don't set do, if I'm reading this correctly. So the people who do are actually most of the people who set EDNS. And I'm thinking this is just the default bind behavior, which is what people who have their own resolver actually use. Some people probably are using some other resolvers that are a little bit more careful and only actually set the thing to 0 if they're not planning to use the DNSSEC, because as you know, one of the big problems to finding out how much DNSSEC is used is that the do bit is useless to signal that. So of those who have the do bit set, how many actually go to the trouble of fetching the DNS key? So a few do, but looking into the domains they fetch them from, you see that basically they are fetching these only for the TLDs. Com, edu, info, org, and the other big one is dlv.isc.org. It's not presented there. I have, okay. There is one last thing that apparently I forgot to add, which was what are the query types? Most people, as you'd expect, ask for A records. Unfortunately, what they get back these days are not A records, but rather C names. About half of the queries asking for A records these days get C names, and that's because, of course, that's how you map things to CDNs and other providers, managed providers, and with varying chain depths, but nothing looks abnormal. 14% of the people actually get answers, valid answers for quad A records. I guess IPv6 is actually going somewhere, which is interesting. And this is a lot more than, for instance, you see queries you see for MX records or PTR or anything else like that. The last slide here is the one on TTLs, which is the one where more things can be learned from. You'll notice that in this graph, the Y scale is not linear. I had to put it into log because otherwise, you didn't see a thing. One of the resolver's functions is to have a cache and a buffer or dampen the impact on servers by answering from the cache. Whether the efficiency of that cache depends highly on the TTL that you get set on the answers you have there. So if you look at the distribution, yes, of course, there are the usual marks where you see bands coalescing, the 1 day, 2 day, 3 day TTLs. But by and far, everyone wants to set their TTL to the least possible amount possible while still providing service. The TTL, like around 0, are about 1,000 times more used than anything else, which kind of defeats the purpose of caches. So, and this is what's worth looking at. What can a resolver do to remain efficient and have an answer on hand to provide to the clients in a situation where everyone is trying to race to as low a TTL as possible? I understand why this is done. I mean, you want to protect yourself from making mistakes, and even more so, have the ability to shift traffic around in near real time. But the effect that you see in a resolver is basically that you have this cache that's basically continually invalidated. So I'll look more at that and see, come back later with the idea is to try to do some simulations of what happens if a resolver decides to ignore the TTL you give me and set different arbitrary values. You tell me a TTL for this data is 0. What if I completely ignore you and decide that I'm going to call it 10, 30, 60, whatever is convenient for me? What impact does that have? In terms of being able to provide a fast answer, but also in terms of if there is an event, how long do I leave my customers in the dark? And other strategies like, well, if I know this thing is going to fetch, can I do a zone transfer perhaps and pre-feed my cache with information that is going to expire? Is there room for a protocol for these special domains that seem to need or desire to be in fast flux all the time? Most of this is legitimate traffic. There was very little that pointed at the low TTLs being only from things like botnets, which of course would use 0 TTLs. But most of this is actually sites that you really want to go to and use. So I'll be looking at that in the near future, and when I have some more results, perhaps I'll come back and tell you more. But it's good to see that you can still come down on some things, but that actually the picture that a resolver is subject to these days is quite different from what, for instance, the assumptions that went into the design of bind. So that's all. Thank you. Oh. Forgot to mention that Comcast was kind enough to sponsor some of this study.
Hi, Joao. Dwayne Wessels from VeriSign. The TTL slide was particularly interesting to me because it's sort of related to a thing that we're doing within RSEC right now. Can you say, like if that was based on the response data, obviously, right? And if a response had multiple records, would you plot the multiple TTL values for all those records, or was that like one TTL chosen per response message, or
For this graph, I only plotted the maximum TTL of that was seen among the different records in the response.
Okay. Okay.
Yeah.
And do you know? I guess maybe it doesn't matter too much, but do you know what that particular result or that recursive name server had its minimum TTL set to? Or
it was the default. It was
the
the bind
maximum
server. It was
TTL
the
it gets?
default, so it honors what it gets.
Okay. All right. Thanks.
Hi, Greg Choules, 3 UK. The trend to smaller and smaller TTLs is obviously a bit worrying as a recursive resolver operator. But from the point of view of the content distributors, is this not a bit self-defeating? Because you might, want to be very mercurial in shifting your content around. This is more of a sort of open point. But if you're forcing DNS queries to take longer because every time you have to go through the chain of, going back to the authoritative server, you're actually slowing the service down for the end user.
You are, in some measure. The thing is, I imagine, these people, the DNS is a small amount of time in the overall picture of what you might have to take to deliver the content that the user is asking for, right? So if by having low TTLs, I can shift the user to some new data center or react to an outage quickly, then perhaps the 0.5 seconds of initial delay for the sort of phone connection might be something that I'm willing to take a hit on in exchange for gaining a little bit more each packet that I deliver after that, the actual video or whatever.
I guess it depends on the content type and how often that needs to be refreshed.
Yeah.
The other point was about the point you made about EDNS.
Yeah.
End users and stub resolvers not using them. I know Apple won't listen to anybody, but is there anything that anybody can do to wave the flag and go, hey guys, please start using it? As operating system vendors, there's absolutely no excuse for you not putting EDNS in as standard. We see it an awful lot. And as response sizes get bigger and bigger, we're the poor guy in the middle that's getting a request that says, I can only support 512, and we get, loads back from the authoritative server, and we have to truncate, they switch to TCP, everything takes longer.
Yeah.
It's a nightmare.
Yeah, I don't know. The little EDNS packets I did see had all the looks from that they were coming from people who were running their own resolvers in their networks, because the buffer size that they negotiated was always 4096, which is the default for bind. There wasn't even a single exception to these things. So I think it's just people set things up, and if they run this way, they run this way. I don't care what they do. For the operating systems, I don't know what it will take to make them implement support for.
As a mobile phone operator, we're talking Apple iOS or Android, and neither of them support it as standard.
Yeah.
It's, we shout, no one listens.
Yeah, I don't know what to do about that.
Hi, Joe. Sebastian Castro from NCRS. About the topic of getting ISP data, we came up with kind of a solution that actually works for us. So basically, we convinced some of the ISPs in New Zealand to give us data, but we gave them a tool for IP anonymization that uses a key.
Yeah.
So they hold the key. They use a key on the IP anonymization tool, and they give us anonymized data that we can actually go and aggregate or analyze. If by any chance during the process we find out something related with an IP address, for example, a malware infection, we go and send them the report. This is the address, and they can use the tool with their key to reverse and find out which are what's the customer.
Yeah, that's useful. I did try that approach with a more standard anonymization tool, like, look, this software is available here.
Yep.
Run it through the data, and then give me that data once it's kind of blurred. It's like, yeah, but we don't know if you can trust that software. It's like, it's there. Anyone can look at it. People are using it. Yeah, but I don't know. We cannot spend the time looking at the software to see if it does what you say it does.
Yeah, on that matter, we have the trust of the ISP, so we're doing that kind of right.
Yeah,
thing,
I
so
mean, you're in
we
a
have an
special position.
advantage.
It's a good solution. And probably, given the little technical understanding out there, the thing about you keep the keys actually might be enough to trigger them into being convinced.
Hello, I'm Bert Hubert of PowerDNS. So since Cloudflare owned up all their nasty tricks, and we can now be proud about that, I can also be proud about the fact that there's a secret feature in the PowerDNS recursor where you can say, do not honor TTLs lower than 60 seconds or 300 seconds or even 1 hour if you feel like it. We built this as a research tool, but we also built it as to help people that are under active denial of service attack. Because one of the easiest ways to relax your server is to tell it the TTL is 1 hour. So we made that feature available so you can change it at runtime without any changes or hiccups. And we did a brief and naughty experiment on a very big place. So we set the minimum TTL to 1 hour for a few minutes. And that dropped the CPU usage by half. And the interesting thing is then we set the TTL to unbounded again, so it could get the actual TTL. And then you see the servers slowly stress out more as the caches expire internally. So this is a naughty feature to have, but I highly recommend that everyone has it because it's a tool in your denial of service arsenal.
Looking at the TTL pattern, it seems to be one of the more effective ones. What you lose in return is something that you should also look at, right?
Yeah, it's not it's naughty, but it's nice. Thank you.
Thank you.
Ola Guemerson, Cloudflare. Can we go back to the slide with the TTLs? Okay. The question I was going to ask you is, have you looked at if there is any, how much reuse there is like of A records and C names that are with a very low TTLs? Because I know that some of my competitors are trying to get around EU cookie policy by having a unique answers to every customer, or every IP address.
I haven't looked at that, but it's a good question.
So,
I'll
lots of the stuff might have no reuse. So
I don't know.
TTL is helping the resolvers throw data away. That's not going to be reused. But I also think that the higher values are also a big problem.
Yeah, they are. The thing is, if you look at it, it's interesting because quite a few people use them. You see the initial spike, but then they are used mostly on sites that no one cares about because this is what you see here is the decay of the TTL in the cache, right? Whenever you get the question for that same domain that had the high TTL. And this is logarithmic. So these things have like 100,000 here. And then what you see people coming back for those sites that have that kind of TTL is like in the tens.
Yeah. And also number of resolvers, for example, unbound restricts by default how long you cache things. So if you set your TTL to over on a day, unbound is not going to honor it.
Yeah.
So
some people
I hope
do.
PowerDNS does that neither.
We restrict to 1 hour.
Maximum?
Oh, no, sorry, no, I think the maximum TTL we do is 1 week.
Okay. So that's still within the band.
Yeah. Okay. Very good. Thank you.
Yeah, welcome.
So while we see also this lower TTL, what puzzles me a bit now, I wanted to know if you also seen that the cache hit rate actually globally seems to still be increasing. I mean, we see numbers south of 90% cache hit rate. Do you all see that with your data?
I haven't looked at that. That's one of the things I want to do, to see when the spike in response time goes up, because you have to do, I don't have access to the internals of the server. I have to extrapolate that from the responses I see on the wire. So the way I have to going to be using to detect that is a spike in the response of something that I was asked previously that now is not in the cache. So I'm going to take longer to answer back from and have a look at that as a measure of detecting. I haven't had the time to do that yet. Okay, thank you very much.
Thank you, Joe. Next, we have an update on experimental bind features for rate limiting recursive queries from Kathy Almond.
So hello. I'm going to run through very quickly, in fact, very, very quickly, as we've gone over this several times already, and most of you here yesterday and all of you here today will have heard about this, the types of attack traffic that's being received by recursive servers. A little bit about mitigation approaches, just for the background, and then I'm going to go through what results we've actually received from some production environments using the experimental techniques that we've been talking about and then playing with for production recursive servers to mitigate the effects of the DDoS traffic on them. And a little bit about the kinds of things that we've been talking about as well internally as ways we could go forward on this. So the attack isn't really intended against the recursive servers at the moment. It's predominantly attack traffic to authoritative servers, but the effect on the resolvers is the thing that we've been focusing on. This type of traffic, I said that I was going to whiz through it, so I shall. Various sources. The original source was the open CPU devices, but there's also bad clients, etc., compromised devices. Symptoms are an increase in traffic generally, an increase in outbound NX domains, so these are clues, and an increase in serve fail responses from recursive servers having difficulty talking to the authoritative servers. So it's bad impact on the clients dealing with the recursive servers that are under attack. Sorry, the authoritative servers that are under attack by the resolvers. The kind of evidence that anybody running a resolver that's under attack will be looking at or should be looking at is the backlog, the clients that are not getting answers because they're not genuine queries that are being sent, they're attack traffic. Possibly look at the outbound sockets because there'll be an increase of resources being used by the resolver. Again, things that you can do, everybody knows about eliminating open resolvers, knows about the CP devices, knows about potentially blocking the bad client sending the traffic. Yep, investigate, deal with them. Things that haven't helped, and I was interested in Ralph's presentation yesterday when he was running the comparative tests under good traffic and attack traffic load. Bind tries very, very hard. In fact, it tries so hard that it shoots itself in the foot sometimes by continuing to try so hard and failing. And the more you increase the resources available to bind, the harder it tries, and then the more it shoots itself in the foot. So that's why the mitigation strategies have been very, very effective. For those running bind resolvers, if you increase the recursive clients limit too high, and you're not running with the with tuning large build, then there's a point where the number of recursive clients that you can have in the backlog then starts to degrade other resources in the server. So a hint to those doing that, don't go too large. About 3,000, 3,500 is probably about it, unless you run with the with tuning large. Some exceptions to blocking clients. Originally, when the attacks started to appear, they would come from so many clients on the network that trying to block them would be like trying to block a flood. The later attack vectors seem to be, the more modern techniques seem to be limited to a few clients sending a lot of packets. So in that case, it might be more useful to block clients, unless of course they're spoofing the addresses within the local space. But it's not quite enough, and we are starting to look at or talk about some other techniques. Okay, what can we do? What have we tried? What do we want to achieve? What's the purpose of doing the mitigation strategies on the recursive servers? So what can we do? The first thing that was tried was lying, essentially. Okay, there's this whole pile of traffic coming in for something that is not giving us answers. So okay, make the recursive server authoritative for the domain, send back NX domain lies, and that then takes the pressure off the recursive server, takes the pressure off the domain under attack. The problem being that it won't be under attack forever, and you're going to need to undo it at some point. You're also responding NX domain to good client queries for that domain, so you've essentially DDoSed the domain locally yourself. And you're probably going to be building up a whole pile of NX. No, ignore that one. That's not true. I was just about to say, and you're going to be building up NX domain in your hash, but you're not because you're answering directly. The next strategy that has been tried is automating this. So, okay, the domain is under attack. How do we know it's under attack? We can look at the queries that are coming in. We could look at the backlog of queries that are not getting answered because the authoritative servers are not responding, and then automate the blacklists. This has been pretty successful, but it tends to produce false positives, so still needs the human touch. Moving on. So what we did try was we thought, well, what do we actually need to do here? We need to protect the recursive server resources. We need to not DDoS the authoritative servers if we can. The symptom of the problem is that the authoritative servers are under attack and therefore have stopped responding, either because they're just collapsing under the weight of traffic, or because we are sending them too much in the way of queries and they have decided that we are the bad guy and started rate limiting us. So the effect on the recursive server is that the authoritative servers have stopped responding in a timely fashion. So we can do some automated tuning based on how the authoritative server responds to the resolver. Tune it either per zone, as in what zone are the queries for, or tune it per server, as in the servers that we're talking to and are not responding. So the fetches per server, which has shown to be the most effective in practical use, monitors the proportion of responses to timeouts and then dynamically adjusts based on that proportion. So when the server's responding well, then the throttle doesn't kick in. When it starts to not respond or serve fail, then at that point the throttle will lower the rate of queries that it will send to it, but still monitor, so we never drop below about 2%. And then when it starts responding again, then you adjust the throttle back up again. So it's dynamic. So when the attack goes away, then the queries start being sent on forwards, which is what I just said. And I believe it's similar-ish to the way that Unbound works in that situation. We provided the fetches per server with a tuning knob, which I think that we will continue to do so, but what defaults we set out with it, we're still talking about. But basically, those are the parameters that are being used for the throttling. So we recompute every 100 queries by default. The first number is what is the point at which we raise the threshold. So if we have got 10% or below, then we raise the threshold. And if we've got 30% or above timeouts, then we reduce it. 5 seconds, thank you. The fetches per zone is a very simplistic one. It's just a standard throttle limit. So if the query rate, if the backlog of queries is above that level, then we start throttling. So this was the first data that we got back, and we were very, very excited because what had been put in place was the fetches per zone limit, not the fetches per server. And what you see here is a trace of responses against requests, and you see the point where the attack traffic kicks in is where the green line starts peaking up and down, and we see that the responses remain steady. What we actually implemented, or what we said we implemented, was that we would start to serve fail prematurely when we got to the point of dropping traffic because the throttle had kicked in. So there is actually a bug in this graph that we didn't notice until later. And the bug is that the requests have gone all over the show, but the serve fail responses are staying nice and neat. So what we actually did was not what we intended to do, but we were very pleased that we did, is we started to drop the responses or drop the clients rather than actually responding. So this shows A, a bug, and B, the throttle kicking in, which is going to turn out to be useful later on. Right. Yes, that shows another view on that, but it also shows that there is, if you look at the graph below, you can see where the responses, the fetches per zone, the zone-based throttling kicked in. But there's also a large amount of grumbling traffic going on behind the scenes. We compared logs on this, and you can see that there is, per the stats that we saw this morning, a lot of background stuff going on that isn't actually kicking the throttles. This was the next graph that we got, the next set of results we got back from another production environment, a different one. And what they deployed first was the fetches per server. But they were monitoring differently. They were most concerned about the degrading performance of their recursive servers, and what they were tracking at that point, and this is the red line, is the backlog of recursive clients. Recursive clients is recursive context. That's where you track that you have a client query, but you have yet to send it a response. So if you've got a large backlog of recursive clients, that's when you're likely to run into trouble. And you can see very clearly the point at which they kicked in the fetches per server. It's the point where the red peaks disappear, but the blue peaks carry on as before, because those are the serve fail responses. And with the fetches per server, we're still sending back a serve fail. The client was going to get a serve fail anyway because the authoritative server is not responding, but we're still sending it back, but we're sending it back immediately per the throttle. So that shows the effectiveness of the fetches per server throttle in this environment. And you can see that it's protected very, very nicely, the recursive server. And it's also similarly not sending those queries onto the authoritative servers and continuing to DDoS them. Similar graphs, but over the same time, this server has also got the per zone throttle as well as the per server throttle. The top graph is the similar graph as I was just showing you, which shows the recursive clients backlog against the serve fail responses. So you can see in the top graph where the per server throttle kicks in, the serve fail responses are still there, but the recursive clients backlog goes down. In the bottom graph at the very beginning, what we're tracking there is inbound queries and outbound responses. And you can see right at the very start of the graph that the per zone throttle had kicked in because the responses back to the clients is lower than the queries inbound. But you can also see there that it is less effective at keeping the recursive clients backlog down. And I think that's because it's a hard limit. The default is 200, but you can tune it to different values. And if you think about this, if you have, say, 5 zones under attack and you're throttling at 200 for the backlog of fetches, then it's never going to go below, say, 1,000. Whereas the fetches per server is going to tune based on the traffic that's going through. So we're hoping that what the user is going to see mostly is situation normal, as in they will get responses to all of their good queries because the server resources are being protected. They might see some serve fail responses to names in zones that are under attack because their good queries for the zones under attack are going to be throttled as much as the bad ones. We're aware that we've not got this quite perfect, and you see some peaks there, and you see some increasing memory utilization in some situations. I'm going to skip through these very, very quickly. What we're thinking about now are things like, is it better to drop or is it better to serve fail? And the likely thing that we will put in the code when we put it out to production release will be to give an option to either serve fail or drop, because drop is good, but serve fail is also good in some situations where you need to signal back to the client. If the client's another forwarder, for example, if you've got a situation where you've got one recursive server and another behind it, which is quite commonly seen in big ISP scenarios, then to just drop on the front, the one that's doing the dialogue with the internet, rather than serve failing back to the one below, it's going to end up DDoSing your frontline server. Serve fail cache, we probably won't put it in the production version yet because we need to do some more fine tuning. The statistics and logging that we put in initially was do it quickest. So we're thinking about improving that. We've thought a lot about and we're talking a lot about the client experience in terms of not DDoSing the zone totally. If you are throttling all the queries for a particular zone that's under attack, then you're throttling the good queries as well. We've talked about using what we have in cache as expired answers, because we know that good answers to queries, that's not NX domain, not serve fail. Good answers are actually a clue to what are actually good queries. So you've potentially got a built-in whitelist capability on the basis of what you had in cache, even though it's expired. So we're talking about that as a possibility going forward. I'm not going to do a summary of techniques because you all know those. And any questions?
All right.
Apparently no questions.
Yeah, thank you, Kathy. And last before lunch, we have the DNS attack resolver loop with Florian Maury.
Hello. So this presentation is about an attack that we named the infinitely delegating name servers attack. That is an attack that allows denial of service attacks against recursive name servers, and there is also a variant of the attack that allows to perform distributed denial of service attacks against arbitrary victims. It was disclosed about 5 months ago, and I'm going to talk about how it works exactly. So just a few words about who I work for, because we're not as well known as all the other companies that spoke earlier. So the ANSI is the French Network and Information Security Agency. That is a governmental agency that works under the authority of the French Prime Minister. And our main missions regarding information system security are the prevention and the defense of governmental systems and also of French critical operators. We have also a mission of information toward the general public and the other entities that I just spoke of. To do that, we study the internet resiliency. You may have heard about the Resiliency Observatory, which is a sub-part of our agency that works on public data about BGP and DNS in order to better understand how the French internet works and to infer how the resiliency status is. And we also work on the DDoS prevention, and that's why we worked on this attack to get it fixed. So just a few DNS reminders so that we can all understand how it works. That's very basic, but well. There are two types of delegation, the glueless ones and the glued delegation. In the glueless delegation, the R data part of the DNS record contains a domain name that is outside of the domain that is in the owner field, owner name field of DNS record. And when a recursive server get that type of delegation, it will put on hold the original query the domain name that is in the R data part. And when it got an IP address, it will query this IP address with the original query. In the glued delegation, the domain name that is in DNS record is inside the domain name, and so the resolver cannot put on hold the original query because it will end up getting the same delegation over and over. So there is, to solve this chicken and egg problem, you have an additional section containing the IP addresses for the name that are in the data part. So how the attack works exactly? So you have the exploitation strategy in a nutshell is that you have a dynamically generated infinite glueless delegation chain. If you look at the top of the slide, you have an example. 1.example.com is delegated to 4.example.com and 5.example.com, which are in turn delegated to 10, 11, 12, 13.example.com. Each of those are also delegating and on and on. And when you have this type of delegations, you end up with an exponential amount of work to do to resolve the domain name. And some vulnerable implementations were following this chain for a very long and sometimes even infinite period of time. So how do you exploit that kind of delegations? You have a sub-resolver that is under the control of the attacker or that is enticed by the attacker to perform an arbitrary query toward the DNS resolver that is the victim of the attack. The DNS resolver will query the root or query its cache and will get to the TLD that will ultimately delegate to one of the authoritative name server under the control of the attacker. When that happens, the authoritative name server of the attacker will answer with the glueless delegation that I just spoke about. And when that happens, the DNS resolver will then query the domain name that are in these glueless delegations. And there you have a self-sustained systems that mean that you can forget all about the other actors. You just have the DNS resolver that will keep on coming to the authoritative name server controlled by the attacker to get more glueless delegations that will lead to get more glueless delegation and on, and you can spin that way sometimes for an infinite period of time. If I try to summarize what I just said, you have an attack that is enabled by a single query and that uses only IRC compliance and individually innocent-looking messages. And the attack is sometimes self-sustained. Some resolvers were implementing a limit, but they were also sending gratuitous queries, for instance, to get the quad A IP addresses, IPv6 addresses, and this was starting once again the attack. So you have a self-sustained system. The impact was temporary or permanent denial of service of the resolver. We'll see about the exact impact in a few slides. But I want to talk about the distributed denial of service variant of the attack. In this case, you have an answer that is containing only glued delegations, in that there is a lot of NS records all pointing to domain names that are right next to the domain name that is queried. And in the additional section, you will put glue record that contain the IP address, either the same IP address or IP addresses that are in the same network prefix as the victim. And this will lead to the recursive server to send a lot of packets to these IP addresses. So how that works exactly, you have the same the attack starts the same as the previous one, and when the authoritative name server of the attacker is queried, it answers with this type of glued delegation. And the DNS resolver will try to send the original query to the DNS resolver, and it will try to send them following the glue's record. So it means that it will send, for instance, up to 16 packets toward the victim. And the victim does not have to be an authoritative name server or a DNS server at all. So sometimes it will not answer at all. And that's not a problem because the DNS resolver sometimes will, I'm not sure why, ask again the authoritative name server of the attacker for new information, maybe because the glueless record, the glue record was incorrect, or some other implementation of sending IPv6 queries to get the information that will lead to more glued delegations, and so to more packets sent to the victim, and you can spin that for a long time. If I try to summarize what I've just said, you have an attack that is enabled still by a single query. That's important because it means that it's very easy to enroll a server into performing this attack. It uses only RC compliant messages. This time it is not really innocent looking because you have a lot of A records, glue records in the additional section. That's some things that you don't see often. And that is interesting because this attack exploits only well-configured name servers. I'm not talking about open resolvers that are ill-configured, or I'm not talking about IP spoofing attacks. Here, the attack works with standard servers and no network tricks. And the attack is once again self-sustained thanks to the gratuitous queries I've just spoke about. The impact is an amplification factor that we in laboratory obtain. We obtain in laboratory an amplification factor of about 10, which is much higher than the average amplification factor that you get from the IDNS 0 large answers that get fragmented. So what are the operational impact of this attack? Well, there was at least 7 vulnerable software that we are aware of, including the major implementations. And it's just interesting to note that Bind was also vulnerable in some authoritative name server scenarios because of the two roles of the Bind server, sometimes being able to be a recursive server, sometimes being able to be an authoritative DNS server. And if you host a domain name that is hostile, you can have a recursive query that is triggered by your authoritative name server, even if you have disabled all the features that are supposed to do the recursive server part. So the exact impact depends, of course, on the implementation. Some implementation were using a lot of CPU to perform to try to resolve these domain names. Some were storing a lot of data in the memory, and I will get back on that. Some were experiencing a cache exhaustion because they were storing the glueless information that are rather useless, and to do that, they were flushing the interesting records that were in the cache. And at least one implementation was very resilient to the attack. So that means that it was capable of handling it and therefore sending a lot of packets because it was trying to resolve the domain name very efficiently. And this generated a lot of network load. And I give a few words about that in the next slide. On at least one implementation, we obtained a permanent denial of service where the resolver will get killed by the kernel because of an out-of-memory exception. So, of course, you can restart the server with a watchdog, but that's still some kind of permanent denial of service. So, just like I said, some recursive servers were very well handling the problem, but some network devices may be overwhelmed on the path of the attack, and therefore we can obtain a denial of service through that kind of traffic. So the obvious potential victims are the out-of-the-box stateful firewalls and the net-based load balancers. The out-of-the-box stateful firewalls, it's interesting to state that it is possible to have a stateful firewalls that is correctly configured and capable of handling DNS traffic, but well. So on the disclosure plan, the original disclosure plan was to contact Google and OpenDNS to get operational feedbacks on our recommendations. That was the feedback that we had from the previous attack that we presented about a year and a half ago, that where our recommendations were not very operational, so we decided to contact them. And I would like to thank OpenDNS that accepted to share with us how they are handling this kind of attacks, and they allowed us also to share it with you and the other vendors. So we once we got this type of information, we contacted ISC and Net Labs and other labs, and we gave them 2 months to get a patch working. We synchronously disclosed on December 8th. However, there were 2 early releases. It's interesting to know that ISC has a disclosure policy that makes them send advisories to their premium clients about a week before the common disclosure date. You may be interested to know that if you have security reports. And Nether Labs also released an early performance patch. The reason for that is that the problem of a slow domain were reported by independently by one of their customers, and that would have been suspicious for them not to release the patch. So they silently released the patch as a performance patch, and later on they explained that was also a security patch. We are completely okay with that, and I would like to thank them because they also worked an extra mile when we were working on this attack. So thank you very much. Concerning feedbacks that we get after the disclosure date, some Linux distributions told us that they were informed a bit late, and sometimes some of them were informed about 2 hours before the disclosure hour. That was rather short for them to work. Well, let us grow up. So the mitigation strategies. It's interesting to observe that the implementations are doing various kinds and very different kinds of algorithms to resolve the domain name. Some are doing depth first search, some are doing breadth first search, and therefore they implement different types of limits. They were implementing different types of limits, and they added some to fix this attack. Some are doing a depth limit, a breadth limit, an overall query time, an overall query count, and also a maximum in-flight query count. And if you observe the column that are the implementations, you see that there is not 2 implementations that actually implementing the same set of countermeasures. And if you look even closer, you can observe that there is, even when they implement limits, they are not using the same values for these limits. All of these limits are working and are thwarting this attack. However, it makes very fuzzy to know what is a working domain name and what is not. So, food for thoughts. So if I try to summarize what I just said, you have an IDNS attack that is exploiting a logic flow in the DNS resolvers that impacts several popular implementations, and that can cause temporary or permanent denial of service attacks on affected system, and also distributed denial of service attacks on third-party systems. It can only be fixed by patching. We are not aware of actually really working workarounds. And of course, if you are using an up-to-date implementations, you are safe. Now, just a few words. All these attacks should have never occurred because the issue was actually documented 30 years ago in the RFC 1034, where we had a sentence telling that the amount of work that the implementation should be willing to do to obtain a domain name and resolve a domain name should be bound in, so that there is nothing that can go south. Even if someone has incorrectly configured some data, or in our case, if an attacker is trying to actively exploit a logic flow. Tony Finch pointing that out on the DNS OARC mailing list. That's interesting because it seems that most vendors were not aware of this sentence or missed it, and actually I didn't see it either. But I don't want to blame anyone because implementing DNS recursive servers is really hard. There is over 200 RFCs specifying the DNS. There are still several active IDTF working groups working on modifying the DNS. That's a lot of things to know about, and there is even more information hidden in the source code of the various implementations, meaning that there is a lot of knowledge that is hidden and not easily accessible. And even if these 200 plus in RFCs, there is room for interpretation, which means that when the specifications fails to specify how an algorithm should work, then the developers have to get creative because they have to implement something. So that makes a lot of things fuzzy and easily breakable. And to do a security analysis of this, it's really hard. And on top of all these RFCs to consider, the implementation have to deal with things that are not really DNS relevant, but there are the performance needs that often leads to use unsafe and low-level languages, which means that you have to handle also all the memory corruptions problem. All of this makes me think that the DNS is like a vulnerable ancestor. You have to look at it in awe and also with great fear, because it is extremely fragile. And you have, for instance, temporary fixes, such as the source port randomization that fixed the Kaminsky attack, but that was insufficient because in some cases, we demonstrated in 2013 that blocking DNS messages allowed to trick the DNS servers and do an easier cache poisoning, even with the source port randomization. So the right answer, of course, is DNSSEC, but if you observe the list of bugs in the recursive servers, you will see that there are a lot of bugs related to the implementation of DNSSEC. So by adding security features, you in fact create holes for availability problems. And the DNS also has to handle things that are not even related to the DNS, such as the DNS rebinding attacks that are in fact browsers attack. But the DNS is the best place to handle this kind of thing. So you end up with a protocol that is rather fragile, loosely specified, and extreme precaution, therefore, should be taken when you modify it. Thank you very much.
Kathy Almond, ISC. It was just a comment. Thank you. It's a really good presentation. I was just a comment on the diversity slide of the solutions. I think it's unsurprising that you see such a breadth of diversity because the underlying implementations are completely different.
Absolutely.
And actually, I think this is a good thing. I don't know what other people think.
It's a good thing in that there is not a single way of doing it that can be exploited and have all the implementation crash or be tricked by the same logic flow. But at the same time, it's really make fuzzy what is broken and what is not. Not broken in terms of security this time, but in terms of availability of the domain, because, well, some will have a depth that is accepted by Unbound and that will not be by bind or well, whatever.
But other tactics built in within the implementations may well help in any case.
Absolutely.
So even though the limits or the way of applying the limits is not the same, there are other factors that are not included there that will impact the outcome.
Absolutely. The message here is really that for security analysts, it's very difficult to have a clear view of the protocol because there is a lot of hidden knowledge in the implementations because the specification is really loose about what is to really do to prevent attacks. That's just the word. But yeah, absolutely, diversity is a good thing, and you'll see in the next presentation that I will do that we encourage diversity. So yeah.
And a tiny, tiny little bit of feedback on management of security issues. Internally, we don't, if we can, release a security notification on a Monday, because that then gives us the scope to do the pre-notifications on a day before, which is not just preceding a weekend, that kind of thing. I don't know whether people behind me will echo the same thing, but our policy is actually to try and avoid releasing on a Monday or a Thursday or a Friday because of the implications to people needing to deploy.
Okay, got it. Thank you.
Hi, thank you. Benno Overeinde, NL Labs. Thank you for your work. It's awkward standing this way. So indeed, about informing the community, and you mentioned the GNU Linux people were, well, only just in time informed. We were in contact with the security officer of FreeBSD, but I understand that's an issue we should talk in a different setting or maybe later on. We're also afraid if we know our customers, we don't know all the BSD or we don't know all the Linux packages. And if we send out a pre-notice, we don't know how the news will spread out through the community. So that's something we have to discuss more seriously, I think. It's a good thing you mentioned. And the other thing, but that's me standing in front of my developers. I'm for sure they are aware of that a query shouldn't result in an infinite amount of work. So I don't know, they read the sentence in the RFC, but they definitely are aware of that. And of course, it was a very specific use case that nobody ever thought about it would happen. And,
to be completely honest, when I contacted Google, their first answer was, "Oh, come on, man, nobody will fall for that."
Yes, it's true. Okay, thank you for your work.
Also, to clarify, Dan Bernstein had this fixed in 1999.
Yep.
Not phenomenon. So we also had that fixed, so we were not vulnerable. But one thing that puzzled me with one of these sorts of attacks, the attacker has to run an authoritative name server that sort of receives a lot of queries also. Have we actually seen that attack in the wild a lot?
Actually, I'm working for the laboratories, so there is a lot of information compartmentalization in our departments, so I'm not aware of the actual attacks that are seen in the wild, so I can answer this question. Sorry.
Carsten Schiefner, DNX, cctld.de. Could you do me a favor and go to your very last slide, the one before the Q&A? Yeah, sorry. That one. Well, because I've seen that phrase, the DNS is fragile. I've heard that at least once. That was a couple of years ago, and it was an announcement by the former CEO and president of ICANN to a bunch of governmental people, and he even added that the DNS can collapse anytime soon. So I just wonder whether, from your point of view, if you need to make a choice between these two options, is the DNS protocol suite, is that fragile, or is rather the implementation of that very protocol suite, is that the fragile part? Or is it really somewhere in between?
I think the DNS as a protocol is rather fragile, because of, well, the loose specification and the creativity. There are nasty good tricks, and there are nasty bad tricks. So, but on top of that, the fact that many implementations are using unsafe and low-level languages means that implementations are also fragile, not in the same way. So,
thanks.
But it is working. We are all here and paid for doing DNS, so yeah, it's working. But
it was just me trying to figure whether you would rather say this is an action item on, say, the IETF to come up with a redefined, reviewed DNS protocol suite, or whether you would rather say this is an action item for implementers, that they should get their stuff together in a better way. So that was just trying to figure out.
If the IETF specifies more and more closely what it should be done, what kind of limits there should be, then the implementations will follow this recommendation, these guidelines, and therefore will get their things in not in order. I'm not judging, but I mean in parallel.
Okay,
I'm not sure. Better word.
Hi, my name is Roy Adams. I work for Nominet. You just mentioned that you haven't seen this attack in the wild.
No, but I haven't access to this kind of data. That's just what I'm saying.
Okay. from what I'm seeing at Nominet, and we inspect this kind of stuff, not specifically this kind of stuff, but when we see what looks like loops, we get interested in, and we try to figure out what's going on. We have not seen this. We can classify a whole lot of things, but we have not seen this. So basically, you found a bug in a corner case that actually, in my humble opinion, doesn't really happen in the wild. And that's now plastered on these slides and for everyone to see. So I just want to put this in the right place. It's not the end of the world. It's like I said, it's a corner case. If you look at the amount of loopings possible, in the past you had resolvers responding to responses, authoritative servers responding to responses. You had CNAME loops, you had DNAME loops, you had packet compression, DNS message compression loops. And I'm sure that anything that's been built after the time that these things were found will have these problems as well. And we now have new implementations since 2005. We have UDIFA. You have not. I'm not saying there's anything wrong with those. They're just more and more implementations coming out, and there's more and more bugs that will be found in this. We need to be very careful not to mix protocol with implementation. So, yeah. I understand. Sorry, I hope you understand. I'm trying to make a point, but now I'm confused what point I'm trying to make. So the thing is, I think it's good that you informed all of these vendors about the individual problems. I don't think it's the end of the world. I don't think. I mean, there was basically too much information for me here in the slides to worry about. So.
The thing about this attack is that it has an impact on all the implementation and all version of the softwares. And that means that there will be a long trail of softwares that won't get updated. Mm-hmm. And the performance in the denial of service attack are a lot better than what you can obtain in the other well-known attacks. So that's not at the end of the world. There is a patch. It's not the DNS protocol is not ultimately broken. Yeah, that's true. However, I think that if you don't see this type of attacks in the wild, it's only because the easier ones are still useful. But the attacker will get better. If we have efficient ways to handle all the previous.
Yeah.
On the contrary of the attack that I presented about a year and a half ago, here it's not far-fetched to imagine a script kiddie running that kind of scripts.
Yeah, they only need your slides to do it. Thank you.
Hi, Andre Sri from CZNIC with my Debian developer hat as a maintainer of several DNS packages. As for the information for the Linux distributions and BSDs, there's OSS security list for distributions that you can use, and there are even not only the Linux distribution and some BSDs on that list, so that's a good place to contact. It's run by OpenWall people, so it's OSS security list something.
Absolutely. Thank you very much. Well, thank you.
All right. Thank you, Florian. And hopefully lunch is ready out there now. Don't forget that there's a DNS, or not DNS, PGP key signing in Mirman at 1 o'clock.
Now that I've reread your email, I'm insulted. Now I have to figure out how to give you like CG and address. Like I was gonna, I asked you how many IP addresses you needed, so you said, you know, you might need like.
I actually think we're all right. We keep better than just 2 IPs because we took one zone up cleanly. Or we can do more. On the network that we run on the West Coast, we have 24. We didn't pass it. We have 4 so when well, we can use that approach to also we take that's you need to do anything. If you would like to do it, would be extremely interesting to explore anything. So please can we have a plan? Okay. Memory.
Test. Yeah. Saturday morning, Sunday morning.
The DNS.
Okay. Oh yeah, because Williams. This is
So that would be an option. If I wanted to do one, I would mount something really like
So you should be able to share your desktop.
Sorry?
I said, so what we're trying to achieve is for you to share your desktop to this machine, yeah? No? No, we're trying to say what we're trying to achieve is the audio that you send in there comes out here, yeah?
Well, I don't say
No, but, right. So
Yeah,
this
so
is
this
joined.
is-
So
yeah.
now,
we want the audio from here to go through the PA.
yes, and we want, and the audio, so we want the audio to come from William's machine to here to the PA, and we want William's screen to come to here.
Yeah.
Or we want the screen of this machine.
Right. Oh, he's not just going to slide share his...
Well, whichever works.
Yeah.
So it sounds. So have you sent him this?
No, I'll have to, because this is still this morning's Hangout, which I left
Okay.
open to do this testing. So I'll need to make a new link and then log into that from here. And
Should there be audio at this point?
Not so far. No. We're
not
trying
yet.
to figure that. So yes, you need to send them the
Whatever the new
URL,
link is, yeah.
and then we can feed that in here.
And I need it here as well. And it's complicated.
Yes, it's complicated. Yeah.
Yeah,
I mean, there's
just
two ways that we can do it. We can either have William's audio coming through and out here, and somebody just paging through the slides that go on the screen, or we can have William share his desktop. Either should work.
Right. Yeah. So when...
Let's see if he's awake.